Thank you. Now I would like to request Professor Sujit Kumar Khuntia sir, Director Curriculum Development, BPUT sir, for delivering the welcome address.
Good morning, all of you. Esteemed chief guest of this inaugural ceremony, Professor Dr. Shiv Kumar Mishra, Director CUPGS, College of Center for UG and PG Studies, that is the campus college of this university. Also, the Dean Faculty of Engineering of BPUT Odisha. Esteemed guest of honor, Professor Manas Ranjan Naik, Professor of Electrical Engineering of Center of UG and PG Studies, BPUT Odisha. Dr. Manoj Kumar Sahu, Associate Professor of Electrical Engineering Department, Center for UG and PG Studies, BPUT Odisha. Also, he is the technical coordinator. Dr. Shashwat Satpathy, the anchor person, he is also the co-coordinator for these technical sessions. And esteemed faculty participants of different affiliated colleges. Ajit Naik, Mr. Ajit Naik, our section officer, Register Section, Office of the Registrar, BPUT Odisha. And dear students, those who are here as volunteers to help us. So, we are conducting, all of you know that this particular faculty development program on electrical machine 2, that is in 4th semester in BTech program. Is it? Achha. From 19 to 23rd for 5 days, and we have invited experts from NIT Raurkela, VSS Bulla, also our professors of our CUPGS, that is the campus college of the university. They will be also taking classes for that program. So what I mean to say here, the vision of the university, the vision of our Honorable Vice Chancellor, Professor Amya Kumar Raut, is very, very clear. That is to upgrade all the stakeholders, be it faculty, students, colleges, and for all. So, because of its proactive initiative, we are taking off number of programs, number of activities. You might be knowing all that. Your students might be participating in all those programs. BPUT Tech Carnival, Project Exhibition, Research Conclave, Hackathon, number of programs for students, faculty, for faculty development programs. Also, we are conducting NBA, workshop on NIRF, National Institutional Ranking Framework, to prepare the colleges in line with, as per the requirement of that ranking framework or accreditation bodies. So, this particular program, I hope, this faculty development program, will definitely enhance your knowledge, domain knowledge in that particular subject. Also, you will come to know, you will learn how to teach in a class from the experienced faculty members, professors, those will be taking classes. You will come to know how to handle the students. You know, as per NEP, now teaching is not a one-sided matter, one-sided affair. What was the practice? Only you are delivering lectures and students are taking notes or listening. So now, as per NEP, it is now student-centric learning or student-centric education. So you have to see that, you have to ensure that students are taking part. You have to make it participatory learning. That you have to ensure, being faculty members, you have to ensure that. You have to see that they are asking questions. You see that, you ensure that that analytical skill, that problem solving skill is developed in the students. That is very, very important. So that will learn how to handle the class, how to involve the participation of the students in a classroom. That will learn also from here, along with the subject knowledge. Definitely this 5 days sessions, there are 10 sessions over the 5 days, will enhance your subject knowledge and help you delivering in a better way to the students. That is the very motto, very purpose for which actually we are taking pen to conduct this, and intentionally we have capped the number to 40. We have allowed 40 faculty members to participate in the program, so that there will be better interaction, better learning, effective learning. Earlier we were conducting program in Bhubaneswar and allowing 100 plus faculty members, but what you observe that programs were not that effective. That teaching learning process were not that effective. So that's why vice chancellors are advised to make it cap it to 40, so that you can participate, you can interact with the experts or resource persons. So that's all. I hope you will all, with all sincerity, attend the sessions and learn for the betterment of yours and also for the betterment of your students. So thank you all of you. Thank you for coming. And
Thank you, sir, for the inspiring and thoughtful words. Now, I would like to welcome Professor Manas Ranjan Naik, sir, guest of honor of this faculty development program, for the address.
Thank you, Shashwat. Respected chief guest, Professor Shivkumar Mishra, Director of CPGS, Deputy Raulkela, and respected our Professor Sujit Kumar Khuntia, Director Curriculum and Development, Deputy, and Dr. Manoj Kumar Sahu, Technical Coordinator of this FDP program, and Dr. Sasho Saraswati, Technical Co-Coordinator of this program. My dear all faculty member participated in this program, dear students and the staff of this university present here, and this is a very useful program for all faculty members. We should enhance our knowledge by participating in faculty development program which are conducted by the university from time to time, and we have planned, as Director CD told, we have planned electrical machine too for this faculty development program at this time, because now the machine 2 is the course in the 4th semester, which is now continuing. That's why we plan will start from the machine 2 syllabus. So here, you know that machine 2 or electrical machine is the backbone of the electrical engineering. You can think from power generation to electric drives. We need renewable energy to electric vehicles. Everywhere, without electrical machines, power system is meaningless. So electrical machine is the backbone of electrical engineering. So a very important subject in electrical engineering. So you have to enhance our knowledge by participating in this program. During this program, you can interact with our resource persons who already we have invited from NIT Raulkela and the BSSUT Bulla, and also some faculty members of our CPGS will interact with you regarding this the syllabus as told by our Director CD. So here in lesson 2, we have planned for synchronous generators or alternators, synchronous motor, three-phase induction motor, single-phase induction motor is available in the 4th semester electrical machine 2 syllabus. And I hope this faculty development program definitely enhance the knowledge of our faculty members who are participating here. They can also give training to the other faculty members who are present in their institute. They can also interact with their other faculty members, and they can also clear doubt of the other faculty members. So this is a good platform where you can clear your doubts and also interact with your faculty members and also interact within yourself also, so that we can give the quality education to the students. And along with the theory, we will also plan for practical exposure, because nowadays teaching without practical exposure is meaningless, because teaching should be industry oriented. Every industry wants the students should be capable of handling the equipments available in the industry. They don't want to give any training at industry level. So it is our responsibility to develop the student in that level, so that the industry will immediately hire them for their employment. So you have to make the student industry ready. So keeping in mind, we have planned here, along with the theory, we have also planned for the 10 experiments, what is already mentioned in the syllabus. We have also planned, and 10 experiments we will discuss here, and along with the theory, whatever mentioned in the syllabus. And I hope this program will definitely give benefit to all the participants who are participating in this program. And I wish all the faculty members for better teaching in future. Thank you.
Thank you, sir, for inspiring us with your thoughtful words. Now, I would like to invite Professor Shiv Kumar Mishra, sir, Director in charge CUPGS and Dean Faculty of Engineering, BPUT Odisha, to deliver his address. Please.
Thank you, Sashwat. Professor Manas Ranjan Naik, Professor and HOD of Electrical Engineering in CUPGS. I hope you know, all of you, what is CUPGS. CUPGS is the campus college of this university. Actually, it is not little known now, because we have started taking students in the year 2022 in the BTech. So our first batch is graduating this year, and I'm sure that this center is going to make a very good name in near future. So Professor Naik is heading the Department of Electrical Engineering. He is also the guest of honor of this event. And Professor Sujit Kumar Kuntia, he is the man behind this FTP. So he is our Director Curriculum. And Dr. Manoj Kumar Sahu, the coordinator of this program, and Sashwat Satpathy, and all my dear colleagues. I would call you colleagues because I happen to be a electrical engineering faculty member. So I feel that you are all my colleagues. So, and the students who have come here to help us, our electrical engineering students, and all the staff members who are present and helping us. So, good morning to all of you. So, as our sir, Sujit sir has told, that the process of teaching has completely changed. I know that in our times we used to have a complete different kind of teaching, right? That was mostly blackboard based. We used to come to the classrooms and listen what the professor or the associate professors or lecturers used to tell us. There is a very little communication between the faculty member and the students in our time. Okay. So I'm talking about the 90s. Things have changed dramatically since then. And but our practical part was very very interactive. As far as I remember, I had done my BTech from a then RSC. So I still remember, going to machine lab is one of the toughest thing in my life. Because when you go to machine lab, you have to prepare. Okay, unless you are fully ready with the circuit diagram, all the equipments, you will not be allowed into the lab. That was the scene. And we used to actually prepare to go to a machine lab when there was a machine lab class. Because everything, starting from the apparatus, what is the requirement, we have to first make it understand to the laboratory assistant. He will first check it, whether we have understood the program and we are using the right kind of equipments. Okay, so that was the scene. So what I meant to say is that during those times, theory and practical were good. I never say it was not interactive, but it is in own way. So, but things have changed. Things have changed. When I have started teaching, more or less it was the same. So I had started teaching in a private engineering college. So we used to give importance to this particular subject, as Manas sir was telling that machines is one of the very important subject in electrical engineering, and probably it was from the since beginning and it will now, because it has not lost its relevance. And in the meeting of the syllabus, BO Board of Studies, many a times suggestions have come that to squeeze the syllabus to make it machine 1, machine 2 to 1. But we actually vehemently opposed it, and we kept the machines 1 and 2 separate. The reason is because we consider that electrical machines is the core of electrical engineering. Okay, things have changed. We all know that technology are coming and it will go. Okay, with the disruption of AI, things have dramatically changed. People are not, reading the textbooks, isn't it? So the point is that whatever technological advances will be there, technological disruptions will be there, but we have to change our method. We have to change our way of, and what is that called? That is called pedagogy. So the pedagogy of teaching, electrical subjects is to be changed. It's to be completely changed, and to make it, time relevant. So that's what we are trying to do it in BPUT, and as sir has already told that under our dynamic leadership of our Vice Chancellor since 2023, okay, we have been conducting several, programs, several events, and the main and only aim is that participative learning. It is not just for the students, but it is also for the faculty members. Because I consider myself always a student, and I love to be a student. Because, when you are a student, you have a chance to learn. I think then when you become a teacher, if you stop learning, then, the world will be stopped for you. So, my sincere advice would be, that please start learning, learn, relearn, unlearn, learn, and relearn. That should be the motive of all of us, because the world is very changing very fast. You have to also adapt to the advanced technologies like AI, and simultaneously we cannot forget the roots. That is the core. The core of engineering, electrical engineering is machines, and we cannot forget that, because most of the things are still, if you still go to a public sector interview after, the students, if they clear a gate and go to a public sector interview, I've seen that at least 40% or 50% of questions are from electrical machines. And when I was teaching this particular subject, I teach power system, and power system is actually starts with the advanced machines, because, synchronous machines and all. So when I ask questions, they do not have the basics, sometimes what I have observed in the students. So basics have to be very clear, and that can be only cleared in electrical machines. And electrical machines is a subject, without the practical it is incomplete. So our teaching should be such that it should go along with the theory. For example, suppose when you are going to teach a particular subject in synchronous machines, okay, so let's say synchronous generator, and if you do not make the students understand about synchronization, what is the concept of synchronization, they will not know, so they cannot relate, they cannot correlate the theory and the practical. So my sincere advice is, please go back to your colleges and make the students learn correlating theory and practical. How it would be possible? You can arrange for industrial trips. Talk to your college. Let them arrange some industrial trips. Let them go to a let's say power plant and fix up a time for actually observe the process of synchronization. I mean, synchronization do not occur here and then. It's a prefixed time. So you have to arrange for this. If a student will actually see the process of synchronization, once in his life, he can always correlate what you are studying in the laboratory. I mean, in the theory. So these kind of things, let them know what is a induction motor, how it likes, what is the ID fan, what is the FD. So these things are very, very important. So my point is that let us not just restrict ourselves to theoretical teaching, but correlate. And very importantly, the modern technologies, take use of the modern technologies to enhance your teaching methods. Okay, take help of the ICT tools. So these things I am sure that in the forthcoming session, because we have invited some very, very experienced resource persons who are very good teachers of electrical engineering, particularly machines. We have selected in that way. So I am sure that they will also share their experience with you, and probably they will also tell you about the pedagogy that has to be adopted. It's very, very important, because things are really going to change. If you are not going to change with the change, change with the change is the buzzword now. You have to change, okay? Because our world is entirely changing. The things are not going to be same. It is because particularly the education sector is completely going to be changed. The way we are teaching, way we are learning, it has already changed. And BPUT are taking step actually to make ourselves, compatible with the changing world. It's very, very important. Okay. So I am sure that this kind of FDPs, thanks to our director of curriculum, that he is actually arranging such type of FDP back to back. Yesterday I think we have completed one FDP, and today we are starting. So this is the way BPUT is now functioning. You please try to. And we are actually in BPUT, we are very less faculty members, but we are still, working day and night, all of us, how to, enhance the quality of this university. And you are all our stakeholders. So please do cooperate us, and making this, BPUT, I think we will be surely, if this is the pace, we are going, I think we are going to make a separate place in the Indian education scenario. We have a separate place. We will have a separate place, because already, we have made records by publishing results in 2 days. It's not a joke. Think of a situation when 45 days, 60 days we used to wait for the results. I myself was director of examination for 8 months. I know how difficult was it to publish results. Not only publish results, we can publish results because of you. Because if you are not there to correct the papers, it would not be very difficult for us to publish the result in time. So that's what saying. Please, you are all our stakeholders, the faculty members, and I call them my colleagues. we are all colleagues. Let us put our hands together to make this university a different one. Okay, that's what, because it has been now, we'll be in the next year, we'll be entering into our silver jubilee year. So we have to mark, जो जिनकी कौन थी छापो छड़ी जीवा हमें. That is we have to do. We have to leave our impression behind. It's very, very important, and you are all going to part of it. Thank you. Once again, I congratulate all of you to come to this. This is very difficult, coming to university, participating in these kind of activities. Okay, but please remember, this is going to be a regular affair now. We are conducting these kind of things. We have chosen this particular subject because it is being offered this semester. Similarly, all other things, and it is also a very important one. Similarly, we are going to conduct all these things in the coming months. Okay, and please do cooperate us. Do come to the university for this kind of participation, and it is definitely going to help you, all of us. Thank you all of us.
I will take 1 minute, permission of all. Let me acknowledge the presence of our expert, Professor Krishna Roy from NIT Raulkela, Department of Electrical Engineering. So, after 5 minutes actually, we will start the technical session. Now I request Dr. Sahu to propose a vote of thanks.
Good morning to all. Respected expert today, Professor Krishna Roy from NIT Raulkela, Professor Sujit Kumar Puntia, Director CD from the Bijupur University of Technology, Professor Shiv Kumar Mishra sir, Director CUPGS, Professor Manas Ranjan Naik, Department Head of Electrical from CUPGS, and my dear participants, students present here. I express my sincere thanks to the experts, Professor Krishna Roy. It takes taking lots of pain by coming here. I hope he will guide all the participants for learning the machine too. I express my sincere thanks to Professor Sujit Kumar Puntia sir for coordinating this type of great program. And I express my heartily thanks to Professor Shiv Kumar Mishra sir for delivering his valuable talks. And I express my heartily thanks to Professor Manas Ranjan Naik sir for giving his important points regarding the electrical machine too. I also thanks all the participants by taking lots of pains from taking various parts of our state to coming here to learn something. I express my thanks to the volunteers, students. They are taking lots of pain to arranging this. So I hope this program will be a grand success. Thank you all. Hare Krishna. Jai Jagannath.
Now inaugural session is over. I request Dr. Phasor to invite our expert with a brief introduction.
Thank you, Professor Manoj Sahu, for the inspiring words. So now we will start the faculty development. So thank you all the professors for your nice and kind words. So to start the faculty development program, I would like to invite Dr. Krishna Roy, Department of Electrical Engineering, National Institute of Technology, Rourkela, to deliver the topic three-phase synchronous generators in electrical machine 2. The topic is three-phase synchronous generators.
Hello. Mic testing. Check 1, 2, 3.
ଦେନ୍ ପଚାରି ପଠେଇବ କେବେ ଏତେ ମଜା ବୁଝିବ ହେଇଯିବ ପିପିଟା ଖୋଲି ଟ୍ରାନ୍ସମିଟ୍ ତ ହେଉଛି ଏଇଟା এই লাইটটাକୁ ଅଫ୍ କରୁନ এই ଲାଇଟ୍ ଦୁଇଟା ଦେଖିଲେ କେଉଁଠି ଥିବ ସେଇଠି ଅଛି
closer. Come closer. I think speaker will not require to come closer. Sir, आगे आइए. ऐसा होता है आगे रख के नहीं आएगा अगर
आई थिंक मैं पूछ लेता हूँ सर स्विमिंग सही है सर थोड़ा सा
Okay. Good morning to all of you. I am Dr. Krishna from NIT Rautela, working as an assistant professor in the Department of Electrical Engineering. So here I will discuss synchronous generator. The syllabus is very big. So my portion, let me show you. So I will start with this alternator types and construction. Then armature windings, winding factor, EMF equation, armature reaction, phasor diagram, and from there concept of synchronous impedance, then open circuit and short circuit tests to determine the synchronous impedance, that is for cylindrical rotor machine, then short circuit ratio, and then we will discuss these three methods to determine the voltage regulation for cylindrical rotor machine like EMF method, MMF method and ZPF method. Then we will discuss this concept of two reaction in case of silent pole type synchronous machine, that is Blondel's theory, and then sleep test to determine these two reactances XT and XQ, and the last one, that is power equations and power angle characteristics. So this is my part, so I will cover this portion. So here I will suggest some textbooks for your reference. Like first one is Theory of Alternating Current Machinery by Alexander S. Langsdorff. Second one, P.S. Bimra. Normally we follow this book, everyone know. And this is the second part of this Bimra's book, Generalized Theory of Electrical Machines. And this one, The Performance and Design of Alternating Current Machines by N.G. Singh. Other books are also there. So these are standard books. You can refer to your students also. Fitzgerald books is there. Nagarath Kothari's book is also there. Many books are now available. Okay. So let us go through this introductory part. So synchronous generator, that is the backbone of our modern society, we know. we will generate electricity by this machine. And there are different types of power plants. You know, this one is a thermal power plant. You can see. So what do they produce? They produce AC voltage or AC electricity. We know. So here, what type of voltage it will produce? Single phase or three phase? Obviously three phase. And what is the input energy here? Input energy is mechanical rotation. Who will produce this mechanical rotation? Some fossil fuel will be used here to generate heat, and that heat will be used to produce steam, and that steam will produce this motion. So here the prime mover is some kind of turbine that will generate this mechanical rotation, and that mechanical rotation will be converted into electrical energy by this alternator. Synchronous generator, synchronous machine, when it operates as a generator, we call it alternator because it produces alternating voltage. Okay, so that is the concept. Next, here you can see one photograph of hydro power station. So here also similar things happen. Only difference is this turbine. Here we will use the pressure head of water, and when we will release that pressure head, it will rotate or pass through the blades of the turbine, that is water turbine, and this same thing, that is mechanical rotation, will be produced, and that will be converted into electricity by this alternator. So here in these two types of power plant, alternator, that is synchronous machine, it is somewhat different. How they are different? In case of steam turbine operated alternator, the turbine is normally known as hydro generator because it runs at very high speed, and later we will see that when the machine runs at high speed, its number of poles will be lesser. Okay, because we have to generate same frequency, that is 50 Hz. In our country, standard frequency is 50 Hz, so we have to generate 50 Hz frequency, whatever may be the running speed of the machine. So in case of thermal power plant, as we will use this steam turbine, so its speed is high, and the alternator type will be turbo generator type, and that runs at higher speed. That is why it is turbo generator. In case of hydro power station, speed is low. So how to achieve this low speed? By keeping frequency fixed, the machine will run at a lower speed. We can do that by increasing number of poles. Okay, and as we have to increase the number of poles, the diameter of the machine will be very large with respect to the other one driven by the steam turbine. Okay, so that is the basic difference of construction. So let us go to the construction here. So this is, we can see a cross-sectional view of a cylindrical rotor type alternator. So this is the schematic diagram. Here you can see three-phase windings which are placed on this static part of the machine, that is the stator, and this field winding that will be placed on the rotor, and it will be supplied from a DC source to produce alternate north-south poles, that is called heteropolar structure. Okay, so the number of poles can be in pair-wise, that is either 2, 4, 6, etc., even number always. So magnetic field system in rotor supplied from DC source and through brush and slip ring. So we need to connect the source, supply source, to this field winding as it is moving. So we need some slipping arrangement. So that is done by this slip ring and brush arrangement. And armature will be on the stator. Okay. So there are some reasons why we will place this armature on stator and field winding on the rotor, that we will discuss. So here the three-phase coils or windings are 120 degree apart from each other in space. That means the windings will be placed in such a way their axis will be 120 degree apart from each other. That means their phase displacement with respect to space. So this is space displacement, not time displacement. So time displacement we will discuss later. So that is the arrangement of the three-phase windings. Now the reasons for placing the field in rotor and armature in stator. So first of all, it is ease of construction because this rotor winding is less complicated because we have to supply DC voltage and only two terminals are sufficient. So DC voltage can easily be supplied to a winding which is having only 2 terminals. Okay, so that is why it is less complicated the field winding, and stator armature winding is on the other hand is little bit complicated because 3 windings are there, 3 phase windings, so 6 terminals. Now we can connect them either in star or in delta. If we connect them delta, then outer terminals will be 3. Okay. If we connect them in star, still we can have 3 terminals, outer terminals, but if we want the star point, then we need another extra terminal. Okay, so a little bit complicated than that of rotor winding or field winding placed on the rotor. Okay. Next, better insulation of armature is possible. Now, if we put the armature winding on rotor, that means it will be rotating. So anything which is rotating, that we need to insulate is little bit tougher than that of if it is on static part. Okay, moving anything is always not that easy to insulate. Okay. So if we can insulate them in a better way, then we can design machines with higher voltage rating, and thicker conductors can be used in armatures. Thicker conductor means lesser resistance, rho L by A. If A is very high, resistance will be lesser, so current rating we can increase by putting armature winding on the stator. Next, number of slip rings required. If we put the field winding on the rotor, only 2 slip rings are sufficient. If we have the armature winding on the rotor, at least 3. Whether it is star connected or delta connected, at least we need 3. In case of star connected, if we want the star point outside, then we need 1 more. So if we put the field winding on the rotor, lesser number of slip rings are required, so cost of the machine will reduce. So only 2 slip rings required to carry the DC to rotor and reduce rotor inertia. The field winding, the field system will have lesser rating than that of armature winding, obviously. So as the voltage and current ratings are less, so we have to put those things on rotor. So in that case, overall size of the rotor will reduce. So we can have a rotor which will have lesser inertia. Okay, so that we can run it with a very high speed. Okay, so high speed machines are possible if we put the field winding on the rotor. Next, improved ventilation. Heating effect due to I2R loss as well as core loss. So that heating must be we need some cooling method to reduce that heating effect, so we need some ventilation. Okay, so now you think anything on rotating part or anything on static part, which one will be more easier to cool? So obviously it is easier to cool anything which is static in nature, because we can have extra cooling arrangement. There are 2 types of cooling arrangement. One is natural cooling, another is forced cooling. So forced cooling is possible if the winding is itself at rest. Okay, so that is why armature windings are on the stator winding, and field winding having lesser ratings will be on the rotor. So if we can arrange all these things, then we can increase the output also. That means overall output of the machine, that means rating of the machine can be increased. We can design high rating machines in MV range, megavolt range. Okay, so now the rotor construction. You know very well that there are 2 types of construction of rotor, cylindrical rotor type, and based on that we name the synchronous machine like cylindrical rotor synchronous machine and salient pole rotor synchronous machine. So this one is cylindrical rotor, this is cross sectional view, this is one rotor, cylindrical rotor you can see. So here on the outer periphery of this rotor you can see slots to put this field winding. So here a 2-pole machine is shown in this diagram. So this will create north pole here and south pole here. By changing the direction of or the polarity of the supply voltage, we can change the position of north-south poles also. Here you can see on the rotor the conductors are not placed exactly parallel to the shaft, because this is a rotating member, so there will be centrifugal force. To reduce that centrifugal force, we use these skewed rotor slots to reduce the centrifugal force. Okay, and this one is the salient pole type structure. So here, one with the in comparison with the previous one, you can see here if we neglect the opening of the slots, the air gap is more or less uniform. So we can consider uniform air gap. And in case of silent pole machine, it is not at all uniform. So at the yes, anything? So at the pole tip region, air gap is very less, but in the interpolar region, air gap is very high. Okay. So due to this non-uniform air gap, the principle of operation of this silent pole type cannot be explained with the whatever principle we will use in case of cylindrical rotor type machine. So here we need one theory, that is Blondel's two reaction theory, that we will discuss. Okay. So this is silent pole type rotor. Now the frequency of generated EMF, we know this formula, F is equals to P ns by 120, where P is the number of poles, ns is synchronous speed. In our country and also in many other countries, the frequency of the standard frequency is 50 Hz. So based on that, we can write the formula for to calculate P. So 120 into 50 by ns. So here we can express ns equals to 120 F by P as well as P equals to 120 F by ns. So there are two variables, so we can select one to calculate the other and vice versa. So if we want larger number of poles, the speed will be lesser. If we want lesser number of poles, the speed will be higher. Okay. So here we can see a constructional view or disassembled view, that is, this is the stator and this is the frame of the stator, and this one is the core, armature core, which will be made using this kind of laminated sheets, that is known as stampings. So here you can see slots to house the three-phase armature winding. So the stator or the armature houses the three-phase armature winding placed inside slots arranged around its inner periphery. So in the inner periphery of the armature core, there will be slots where these armature windings are placed. And to minimize core losses, the armature is made of silicon steel laminations. So actually, core losses, there are two components. One is hysteresis, another is eddy current loss. So to reduce hysteresis loss, we will use better material, okay, which will have this its better magnetic property, B and H relation. And in case of this other one, that is eddy current loss, we will require this laminated core. Okay, it will increase the effective length of the path of eddy current, thereby increasing this effective resistance, and hence the core loss will be reduced. So the laminations are usually less than 0.5 millimeter thick. These laminations are insulated from each other by some insulating material like paper, varnish or enamel. And stampings may also have radial and axial ventilating ducts to enhance cooling. As I have mentioned, for forced cooling for higher rated machines, this some ventilating duct will be used. Normally we use this forced air cooling can be there, and sometimes if the rating is very high, in that case hydrogen gas having specific heat 14.5 times more than air is often used. So to flow this kind of cooling agent, we need some passage. That is why this ventilating duct, that means holes will be there. And this whole entire arrangement, that is this armature core and the armature windings in those slots of the armature core, is arranged in a cast iron frame, inside a cast iron frame, as we have seen from that diagram. So that is all about this construction. So let us go to next topic. Any doubt, any question? Construction is basically a little bit informative type, so you may find it little boring.
Sir, in the cylindrical type, the rotor is supplied with a DC supply, but the slots are not throughout the rotor. It is on the some part of the rotor.
Yes.
So that one part, one side becomes north pole and other becomes south pole.
No, that
Depending
is-
upon the pole.
Yeah, that is not the reason actually. Actual reason is we need to create a specific pole at some specific region. So it is better to keep that part without any slot openings. So that is the reason. So if it is 4 pole, then arrangement will be little bit different.
Sir, while the skewing is done, does it
Yes,
provide?
yes. Where is it? So let us consider cylindrical rotor. So this will be the shaft. So if we place the conductor exactly parallel to the rotor, shaft, sorry. So what will happen? The centrifugal force is always outward from the center. So let us consider this is the direction. So here also it will be at this direction. Now consider the case of skewing, somewhat like this. So again, the direction here will be somewhere here, but here it is not in this direction, somewhere here. So when we consider the centrifugal force parallel to this shaft only, so suppose this one will give its whole contribution, but this one will give you a part of it, depending on the angle. So cosine component or sine component, whatever. So that is less, isn't it? So if we
cling on to it, it will
Yes.
cling on to it.
yes, so if we consider every point, so at every point we will get some different value of centrifugal force which is less than its actual value. If we place it exactly parallel. So overall, if you sum all of them, overall centrifugal force will be little bit lesser. Am I clear or not?
Sir, is there any problem for magnetic locking?
That is another point. That is in case of motoring mode.
Not.
Yes.
What are exactly the noise?
Sorry?
Noise? Humming is also reduced. Noise.
Noise will be lesser.
Humming sound is also reduced.
Yes.
This skewing also acts as kind of a damping.
Yes.
Pseudo damping.
Yes. So all those are in motoring mode, not in generating.
Not in generator, okay.
Yes.
It is induction motor only.
Yes, yes.
Maintenance wise going is doing.
Yes, yes.
Reducing the magnetic locking as well as the humming.
Yes. So all those are for motoring mode. Okay. So next is armature windings, winding factor, EMF equation. So armature winding. So armature winding, that means conductors are connected to form a coil, a particular coil, and all those coils can be connected in different way to form a particular phase winding. Okay. So there are different ways of connecting, but normally used connections are lap and wave winding. Okay. So in polyphase windings, it is essential that the generated EMFs of all the phases are equal magnitude. These are the requirements to have a balanced voltage system. Okay. So magnitude has to be equal. Then the waveforms of the phase EMFs are identical to each other, and then the frequency of the phase EMFs are equal. And this fourth one is very important. The phase EMFs have mutual time displacement of beta equals to 2 pi by m radians, where m is the number of phases. So if it is 3 phase, so 2 pi by m, that will give you 120 degree. Okay. So these are the requirements for a polyphase windings. EMF induced in a polyphase windings to have a balanced voltage system.
Sir, what is that AM?
M is number of phases.
No, AM.
Number of phases.
Phases.
Yes. Okay. So this is a waveform of 3-phase voltage. You can see. So here you can see all those conditions are satisfied. That means they are having equal magnitude. They are 120 degree apart from each other. So this displacement is time displacement. Okay. And their frequency is also same. Okay. Now phase spread. This phase spread, it is very, one important point or property of winding. This phase, while designing any armature winding, we have to select the phase spread. Okay, based on that, our winding will perform. So what is this phase spread? So consider this two-pole machine having 12 slots. Okay. So depending on the position of the rotor, in each conductor, conductor in each slot will have its own EMF. Okay. So let us see this orientation of this EMF. So as whatever time instant it is showing in this diagram, this conductor 1, it is facing maximum n pole flux. Okay. So it will give some EMF which will align along this direction. So let us consider that E1. So next, after some angle, the conductor 2 is there, so its EMF will lie along this direction, that means along this direction. Okay, so there will be some phase angle difference. We will calculate that phase angle difference. So for the timing, let us consider this. So there are 4 EMFs. So these 4 EMFs can be added to get one resultant. So this is for phase A. So that will give you the phase A voltage. Same way, we can consider the next 4 EMF and we will get phase B voltage, and the next 4 will give you the phase C voltage. So here 3 resultants, so we can get the 3 EMFs, and they are 120 degree apart from each other in space as well as in time. Okay, so now this another point, that is slot angular pitch. What is this slot angular pitch? That is the angular distance between 2 adjacent slots. So here a 2-pole machine, so angle from north pole to south pole, that is 180 degree, 1 pole pitch, and number of slots per pole, that is 12 divided by 2, so that is 6. So it will give you 30 degree, which means angle between 2 slots in this machine is 30 degree. So that is slot angular pitch, or simply slot pitch. Okay.
180 degree is the electrical region.
For this machine, electrical and mechanical are same, as number of poles are 2.
Number of poles are same.
Yes. So now we have to note that for this machine only, it is not generalized. So 12 conductors are grouped in 3 phases, A, B, C. Space angle covered by each phase is 120 degree. So as I have mentioned, this EA, EB, EC, these 3 resultant voltages, they are 120 degree apart from each other in phase as well as in time. In space as well as in time. Okay.
Sir, but when the rotor is rotating, the EA and EB and EC will also rotate along it.
Sorry, EA and EB will also rotate. No. Why they will rotate?
Because the rotor is rotating, so the north pole is rotating always. So
But at any particular instant of time, any conductor.
Okay, yes, sir. Yes, sir.
Little slow. Have you seen the syllabus? I have to cover the whole section. Huh? Okay, I will try. Okay, so time phase angle between EMFs E, B, C is also 120 degree. And now we will discuss this phase belt. What is a phase belt? These conductors 1, 2, 3 and 4 is one phase belt. So all these 4 slots, adjacent 4 slots, belong to phase A. That is one phase belt. Okay. And the combination of 4 conductors in adjacent slots is called phase band, phase belt, or phase group. Okay. Now this is true only for this machine, this particular example. It is not generalized. I will give you the generalized expression or definition. So for this machine, these 4 conductors belongs to any particular phase. Here is phase A, that will form a phase belt or a group actually. Okay. So now, so in general, phase belt is defined as the group of adjacent slots belong to one phase under one pole pair. That is the generalized one. So if we change the number of slots, number of poles, then it will vary.
Sir, I have one doubt. So when the rotor is rotating, the north pole is rotating, but the value of E1 will be maximum when the north pole is aligned to slot number 1 in the stator. But the magnitude of E1 will also change when the north rotor is rotating.
Here we are not considering the variation.
Okay.
Here we are considering all the phases. Phases means at any particular instant of time, we have freezed that sinusoidal variation. Time component is eliminated.
Only the space.
Only the phase.
Okay.
So what is a phasor? A phasor is a complex number which is having some magnitude and some angle. There is no time variation. So we have freezed the time instant.
Okay.
So all these are phasors. Okay.
Sir,
Yes.
E1 and E2 and E3 and E4, all these are the EMFs that has been generated from the slot
Contact.
1, 2, 3 and 4.
Ah.
That is the number of slots per pole. Like this.
Yes. So, what is now the phase spread? We have defined that phase belt, phase group, whatever. So, what is this phase spread? That group of conductors that will occupy a certain portion of the circumference of the stator core or few number of slots. That angle is called the phase spread. So the angle subtended by one phase belt or phase group or phase band, that is called the phase spread. I will show you some examples of this winding design. There you will have a clear idea about this phase spread. Okay, so phase spread of winding is the portion of the circumference of the armature by one phase. Okay.
Sir, that is in between north, south one phase, south, north another phase?
No, it is not like that. In that case, if two poles are there, so we will have only two phases. That is not the concept. So in a three-phase machine, the windings are designed in such a way that a particular group of conductors will form a phase winding, another particular group will form the phase 3. Their axis will be 120 degree apart from each other. So based on their position and the rotor position, that means whatever flux it is facing, they will produce different at that particular instant of time, different magnitude of EMFs. Okay, we have seen the variation, no? Yes, voltage waveform.
Sir, phase spread is always 120 degree?
No. That is what I am asking, coming. Okay. So in this diagram, you can see phase spread is 60 degree only. That depends on entirely you, how you want to design your machine. Okay, see in this machine, phase spread is 60 degree. So here, slot 1 and 2, that belongs to phase A, we can say, let us assume that. Okay, next we have some other phase, next we have some other phase. So here we have not defined the phases, we have classified the 6 groups, phase groups, A, B, C, D, etc., etc. We will classify them as phases later on. So 12 EMFs. So in this case, total 6 phase groups will be there. So 1, 2, this is, let us say this is voltage A. So 3 and 4, this is voltage B. In this way, we will get 6 resultants. So now, taking this 6, taking 2 at a time, we can form one phase. Okay. So suppose if we want to form one phase taking this one and this one. So this one you have to draw a piece here and then you have to find the resultant. In that way, you will get the one phase voltage. Okay. So next is coil span or coil pitch. So first of all, let us define pole pitch. So what is pole pitch? In case of two-pole machine, it is very easy to define. So this distance we can say one pole pitch, right? Now if it is 4 pole, then how to define pole pitch? Sorry.
In terms of angle, it is 180 degrees, sir, in two pole machine.
Which angle?
Between the poles.
we have to specify the point. Okay, so it is a 4-pole machine, right? So what do we mean by pole pitch? So it is the angular displacement distance between two similar points of two adjacent poles. Two similar points of two adjacent poles. So similar points means let us consider two interpolar, pole center. So this distance is 1 pole pitch. Same way, if we take this pole tip, then we have to consider this pole tip. So this distance is 1 pole pitch. If we consider two interpolar regions, then this distance is also 1 pole pitch. So in a 2-pole machine, it is always 180 degree electrical as well as mechanical. For 4-pole machine, it is always 180 degree. I mean, for any number of poles, it is always 180 degree electrical, but mechanical degree will be different. That you can calculate using that formula.
So is it calculate the number of conductors in between them?
No, that I am coming. That is not pole pitch, that is coil pitch. Okay. Pole pitch is distance between two similar points of two adjacent poles. Okay. So that is the generalized definition. It is applicable to any configuration, whether the number of poles are 2, 4, 6, etc. etc. Okay. So now we will define this coil span of coil pitch. Okay. This coil span or coil pitch may be equal to pole pitch or not. If it is equal to pole pitch, then we will call it full pitch coil. If it is less than pole pitch, short pitched coil or corded coil. If it is more than pole pitch, we call it over pitched coil. Okay. So that I am coming. So coil span or coil pitch is the distance between two coil sides of a single coil. Distance between two coil sides. We don't know where those coil sides are placed, whether it is exactly under the same position of two adjacent poles or not. We don't know. It is the distance between two sides of any coil. Distance between two coil sides of any coil. Now coil span is measured in terms of electrical degrees, coil sides or slots. Now we can measure. Okay. So if we want to measure it in electrical degrees, then we have to compare it with pole pitch, whether it is exactly equal to pole pitch or not. Then coil sides. After how many slots? After how many slots the second side is there? Second side is placed. That we can count. Okay. So suppose the coil pitch is 6. So if we consider this one as this one as slot number 1. So 1 plus 6. So at 7th slot, the second side will be there to have a full pitch coil. Okay. So this is a full pitch coil. You can see this is one north pole, one south pole. So that is two centers of these two poles are considered. So after one pole pitch apart, this coil side A and A dash are placed. So coil span is pi electrical degree, that is 180 degree. So this is a full pitch coil. So when the two coil sides are placed exactly one pole pitch apart, it will be called as a full pitch coil. Okay. So pole pitch equal to coil span or coil pitch, then it is full pitch coil. Short pitch coil, as you can see, it is not placed exactly one pole pitch apart. It is slightly less. So this type of coil is called short pitched coil. So here the relation is coil span is less than pole pitch, and coil span is equals to pole pitch minus this epsilon. So what is this epsilon? That is called the cording angle. Okay. So what is this cording angle? That is the angle by which it is departed or departs from this pole pitch. Okay. So when coil pitch is defined in terms of pole pitch, the angle by which it departs from pole pitch, that angle is called the cording angle. Okay. And we know that there are certain advantages of this having this short pitched coil. Normally short pitched coils are used. So if we compare with the earlier diagram, you can see this section of this coil is called overhang or end connection. So length of overhang from this point to this point is greater in case of full pitch coil than that of this next one, that is short pitched coil. You see, this length is less, so we will be requiring lesser copper to build this winding. So it is economical, and by selecting this angle of cording, we can eliminate certain harmonics also. Okay. So that there is one technique using this one factor. If we use short pitch coil, one factor will come, that is called pitch factor. That also we will derive. So that pitch factor, by designing this angle, proper angle, we can eliminate certain harmonics from the waveform of the voltages. Okay. Yes, any doubt? So now we will see some examples of this integral slot winding. So let us consider a 3-phase machine with 12 slots and 2 poles. So 12 slots, 2 poles. Pole pitch, let us consider 6 slots per pole, that is 180 degrees. So pole pitch is equal to slot pitch. Okay. Then coil pitch equal to pole pitch. Slot angular pitch, that is again this 180 degree divided by 6 will give you 30 degree. And phase spread is 60 degree. You have assumed, it is not given. While you will be designing, you have the option to take or select this phase spread. So number of adjacent slots of any phase. So now phase spread is 60 degree and angle between two adjacent slots, that is 30 degree. So let us consider, this is one slot, this is another slot. So this angle is 30 degree, this angle is also 30 degree, and you have selected phase spread as 60 degree. So this makes one phase spread, so that is for phase A, suppose. So now you have another 2 conductors or 2 slots for another phase. So which phase will be here? Next 2 slots, can you guess which phase will be here? Is it B? Huh? It is not B. B will come after 120 degrees, right? So it will be C, but not this. There are, if we use, if we consider conductors, one go and one return. If these 2 are go, then these 2 will come return conductors. That we can see by designing the whole winding. Okay. So let us consider this one. So phase spread is 60 degree. Meaning of phase spread is clear now. So if we use double layer winding, then we can design in this way. So phase A, 1 and 2, slot number 1 and 2 will contain conductors belong to phase A. Then what will be the bottom coil sides? See the coil pitch, that is 6. So 1 plus 6, 7, 2 plus 6, 8. So that will give you 7 and 8. Now these 2 are return conductors. So in slot number 7 and 8, bottom conductors, that is return conductors, 7 and 8 will be return conductors or bottom conductors. That means if we consider this slot having 2 sections, one upper section and one bottom section, then this is upper section, this is bottom section. So this upper section will have this conductor 1 here, and in slot number 7 and 8, this bottom part will have 7 and 8. Normally we put a dash to differentiate the go conductors and return conductors. So next phase B. See, after 120 degree phase B will start. So which slot will contain phase B conductor go? Calculate each slot 30 degree. So 120 degree means 4. So after 4, this B phase will start. So slot number 5. So 5 and 6. Again 5 plus 6 will give you 11, and 6 plus 6 will give you 12. So 11 and 12, these 2 are bottom conductors. For phase B, 5 and 6 are top conductors, upper conductors. 11 and 12 will have bottom conductors. Okay. Now C. So C will start after another 120 degree. So 6, another 120 degree means 9. So 9 plus 10. Now can you find the bottom coil sides for this phase C?
15 and 16.
Is it? Is it possible? How many slots are there? Only 12 slots are there. So it is not possible. So you have to subtract 12.
3 and
4. Exactly. Okay, now you see 3 and 4, slot number 3 and 4. In between A and B, 2 slots are gap, 3 and 4, but these 3 and 4 are actually bottom conductors. So the C will start from 3 and 4, that is true, but from bottom side. Okay, so when you will be designing this winding, first you will design A, then you will design B, then you will design C in reverse direction, starting from 3 and 4. But those are dashed conductors or bottom conductors. In that way you will approach. Consider the same example taking phase spread 120 degree. So now his phase spread is 120 degree. What is the meaning of this phase spread 120 degree? How many slots will be there for phase A? Here we have only 2 for phase spread 60. 4. This whole 120 degree will be for phase A. So see, in this way this design will vary. Okay. So if you take 120 degree phase spread, the design will be completely different. So number of adjacent slots of any phase, that is 4. So again double layer winding. So top coil sides for phase A are 1, 2, 3, 4. Next bottom sides calculation will remain same. Pole pitch is 6. Pole pitch equal to coil pitch. So 1 plus 6 will give you 7, 8, 9, 10. And phase B will start after 120 degree. That is from 5. Now it will start from 5. So 5, 6, 7, 8. And 11, 12, 1, 2. Now these 1, 2 are dashed, bottom side conductors. For phase C, it will start from 9, 10, 11, 12 and 3, 4, 5, 6. So these are bottom conductors. So in this way it will go clockwise and you will form the winding. And for fractional pitch, means that short pitched one. See the difference? Slot pitch, pole pitch is 6 slots, but coil pitch is 5 by 6 of pole pitch. That is 150 degree. So what is the coil pitch? Coil pitch will be 5. So which means if we put conductor 1 here, then next conductor will be 1 plus 5, not 6. In that way we will form the winding table. Phase spread is 60. So here you can see phase A, that is 1, 2, but here it is 6 and 7. 1 plus 5, 2 plus 5. Because coil pitch is 5 by 6 of pole pitch, 150 degree, which means 5 slots. Okay, so next conductor or return conductor will be at 6 and 7, not 7 and 8. That is, in this way we can form this short pitched coil. Very simple. The rest is same way. Any doubt, any question?
Just can you tell once again about the coil pitch and pole pitch?
Coil pitch.
Just
See, this is the pole pitch. Distance between two similar points of two adjacent poles. So if we put one conductor, suppose this is conductor 1 here, and the return path, suppose that coil number 1 plus 6 is 7, 7 here, 7 dashed actually, then this is one full pitch coil. Okay.
180 degree electrical.
Yes. Now in place of here, if we place here 6, it is not just one pole pitch apart, then it is short pitch. After 5 slots, we are putting the return conductor at 6, slot number 6, then it is short pitch. If we put here, then it will be over pitched. More than 5, more than 6. Okay, now the EMF.
Sir, you can. So you can use this.
let me finish this one. Huh? Derivation of EMF you know very well. So, very little things to discuss. So let us consider this elementary alternator having two poles and one concentrated winding. So here you have to understand the concentrated winding and distributed winding. So what is a concentrated winding? A winding whose all the turns have the same axis, center of axis. Then it will be called as a concentrated winding. Where we use this concentrated winding? Field winding of DC machine, field winding of alternator, transformer, all are concentrated winding, having same axis. Okay. Now distributed winding. Where we use distributed winding? Armature of synchronous machine, armature of DC machine, armature of, stator winding of induction motors, where their axis, axis is not at the, all the loops will not have same axis. All the coils will not have same axis. Those are distributed winding. Okay. So here for elementary alternator we have considered one concentrated winding. That means all the turns will have same axis. This is the axis. Okay. So let us consider N be the total number of turns in that coil and Ns, small ns, RPS, revolution per second, that is the speed of the rotation of this rotor. That means that coil is rotating, fields are stationary. Okay, field produced by this NS pole is stationary. So there will be some relative motion, and first of all let us see how much flux is crossing this AB plane. So here flux produced by this north pole will come out through this pole face and crosses the air gap, enters the armature, and then it crosses this plane AB and then again crosses this air gap and enters this south pole. That is the path of the flux. Okay. So here flux density will be phi. So at any instant of time the flux crosses this AB plane is phi, and area of cross section, area of that plane can be calculated as the product of diameter of this coil, which is from this point to this point, and length, that is this length. So if we multiply that, we will get one rectangle. So through that rectangular plane AB, the amount of flux crossing is phi. So flux per unit area, that will give you the flux density. Okay, so this is the flux density. And so here if we consider at any other instant like this one and this one, why we are considering this instant? Because we have considered that this is the one conductor and this is another conductor, and its plane is not exactly perpendicular to the direction of the flux. So it is making some angle with the earlier plane AB, that is which was perpendicular to the direction of flux. So that angle is theta. So now flux passing through this plane of the coil will be given by this formula, that is phi equals to phi cos theta, due to this angular displacement. So in that case, using this Faraday's law of electromagnetic induction or Lenz's equation, we can find the EMF in instantaneous value using this formula n d phi dt with a negative sign, and that will give you this. So EM equals to this and the RMS value is this. Okay. If we take the value of pi as 3.14 and multiply with this root 2, you will get 4.44. You know it is very well. Okay. So that is the expression for induced EMF for this elementary alternator having a concentrated winding. Please remember, concentrated winding. Okay. So now if we consider a multipolar alternator, then what will happen? In case of multipolar winding, so let us consider this two-pole machine. It will give you a flux density like this, and you will get a waveform of induced EMF same as that of flux density waveform, no problem. Okay. But if we take a multipolar machine, say 4-pole machine, in that case you will get a flux density distribution having 2 cycles per revolution. You will get exactly same waveform of that voltage, for that voltage, like this flux density waveform. So here you can see per 1 revolution you are getting 2 cycles. Okay. So the point is you have to define frequency from here. So that is the frequency. So F can be defined as P ns by 2, where P is the number of poles, this ns is in RPS, and if we convert that into RPM, you have to divide this ns by 60. So P capital Ns by 120, and using this value we can modify the earlier EMF equation like this one. So multiplying that EMF for 2-pole machine by this P by 2, then we get P by 2 ns, that is actually F. So F is replaced. Now the RMS value will be like this. Okay, so this is more generalized. Earlier in place of F it was ns, revolution per second. Now we have F. So this one is the generalized equation.
We want to learn or something or
Okay, let us take a break.
Hello. Excuse me, everyone have joined the WhatsApp group or not? Is there anyone who haven't joined? Anyone who haven't joined till now? Four. Okay. Just scan the QR code.
बड़ा कर दे फुल स्क्रीन कर दे फुल स्क्रीन सुन सुन सेटा खोलो ना हे सेटा खोलो फोटोटा खोलो ना फुल स्क्रीन मार आउथरे हे कि साइन इन मारना डाकी दे
Excuse me, everyone has signed this attendance sheet or not?
यहाँ पे कार ब्लैंक अच्छी डाकी दे खेलो कोट हो आस्तान सब की कॉलेज में बड़ा
एरा 23 जन करना बॉडी नंबर भाई गोटे मिनट
डाकी दे दिया जा
1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 21 22 23 24 25 तो एक्स्ट्रा लिखी छी 25 ठीक अछि एक्यूरेट सब साइड
अबे डी टेक्नो स्कूल एटा कोन बे
कि मुगी नै ये प्रेस के जे तो खाई पड़ती ଏବେ ଏସିଟା ବଢ଼ାର ଗରମ ଲାଗିଲାଣି
ଦି ଭାଇ ଏଇଟା କି ସ୍କୁଲ ଏଟା ତ ନୂଆ ନୂଆ ଦେଖ ସ୍ପିନ୍ ଡ୍ରପ୍ ପନିକ
କୋଉଠି ଅଛି ଦେଖ ନା
କିଏ ଜାଣିଛି ଭାଇ କୋଉଠି ଅଛି
ଏଟା ତ ଅନଗୋଲ୍ଡ ଥିଲା ଗୋଟେ ଆଦର୍ଶ ଦେ ତା ଆଦର୍ଶ ରାୟଗଡ଼ାରୁ ବି ଆସିଛି
କୁଆଡ଼ୁ କୁଆଡ଼ୁ ଆସୁଛନ୍ତି ଆଦର୍ଶ
जो
କଲେଜ।
पहला देखो तो पहला किट भाग देख लो कलर पीपीटी खोल दे पीपीटी खोल सब जॉइन कर दे
ଶୁଣୁ ସେଇ ପିପିଡ଼ିଟାକୁ ପଳା ଯେଉଁଠି ଛାଡ଼ିଥିଲେ ସେ ପିପିଡ଼ିଟା ଆଉ ଗୋଟେ ପିପିଡ଼ିଟା ହଁ ସେଇଟା ଫୁଲ୍ ସ୍କ୍ରିନ୍ ମାରିଦେଇକି ରଖିଦେଇଥା ହଁ ସ୍ଲାଇଡ୍ସ
कई इधर है कार बंद पोर्टेबल बाइक पीछे अरेंजमेंट है सब कैंटीन पर चलने के लिए
କରିବା
जूस भी लगी तो खाएगा तुम 3:30 क्लास अच्छी ना 3:30 इधर साइको मास्टर
ଏଇ କାଲି ରହିବ ଫାର୍ଷ୍ଟ ହାଫ୍ ରହିବ
रही मुझे प्रॉब्लम नहीं आज ही अच्छी काली भी फर्स्ट हाफ खाली 2टा क्लास अच्छी एंड में गुटे ही कुकुर मार रहा है अरेडा साइको
ଫାର୍ଷ୍ଟ ହାଫ୍ ରହିବ
ମନୋଜ।
ହେଲା ମୁଁ ପଳେଇବି କିନ୍ତୁ ସେଟଅପ୍ କରିକି
कौन कोडी
ଅଛି କାମ ଅଛି
एटा रहबा कारण छै तुम थोड़े सेटअप करले कुछ करवा नहीं बस तुम
ଏମିତି ତ ସେଟା ତ ଚାଲିଛି ଏମିତି
तो देखो
ପଜ୍ ମାରିବ କି ଥାଉ ମାର
था ऑन तो
ଏଇଟା
ଏଇଟା ବନ୍ଦ କରିଦେ।
ସରି ଏଇଟା ଖାଲି ଦେଇଦିଏ
ऑडियो बंद कर देता
ଅଡ଼ିଓ ବି ଯାଉନି କି ମାଇକ୍ ସେ ଅନ୍ ଥିଲେ ସିନା ଯିବ
हाथ केमती जाउतला
କୋଉଠି ଯାଉଛି
सेतेबेले जाउतला देखुतला ऑडियो इनपुट
ଯାଉଥିଲା
हां सेते देखो नथला हमें कोटली जो माइक रे कैमरा माइक लगी जी मन नहीं एबे देखो नहीं
ଏଇଟା ହେଲେ ତ ଏଇଟା ହେଇଯିବ ବନ୍ଦ ଥିବ ମ ଏଇଟା ହିଁ ମାରିଦେଲେ ହେବ ଯେ ମ୍ୟୁଟ୍
थाओ प्ले सम म्यूजिक କିଛି ବି ବାଜୁ ଥାଉ
ସେଇଠି ବଜା ସେଇଟା କନେକ୍ଟ ଥିବ ବଜାଅ ନା ବଜାଅ ଯଦି ବଜାରେ ସେ ବଜେଇ ଦିଅ
ମୁଁ ମାଇକ୍ ଅନ୍ କରି ମୋର ଫୋନ୍ ବଜେଇ ଦେବି ତାନୁ ହେତ୍କି ଦୂରକୁ ଉଠିକି ଯିବ फिर तो देखिए इडली बड़ा खाएगा फिर इडली बड़ा खाएगा और बाड़ा वागी लागू जी खटा खटा लगी जाଉଛି मागे गोबरा में सोला सोला में ना यस ला केन ଅଛି ତାର आउटलेट
କ'ଣ କି
गोबरा में आउटलेट कोडी ଅଛି
କୋଇଲ ନଗର ପରା
ଓ ଏତେ ଦୂର ଆସିଛି
ଏଇ ତ ପାଖରେ କୋଇଲ ନଗର ଆଉ ତୁ ଦୂର କହୁଛୁ
इंडिगो तो भले एसआईएस को जो पिपीडा का तो ये इंडिगो वाला
छी
ସବୁଠୁ ବେଷ୍ଟ ଥିଲା ବିଏମ୍ଆଇସିରେ
से कसम
ना ना
କନଫରେନ୍ସ
ଆମେ
ଖାଇନ
ଏମଆଇଟି ଯାଇଥିଲୁ
ତମେ କନଫରେନ୍ସ ଖାଇନ
ଏମଆଇଟି ଯାଇଥିଲୁ କାର୍ଡ ଦେଇଛ ଗାର୍ଲିକ ନାନ୍ କୁ ବଟର
ଭାଇ।
ଚିକେନ
सेटा एनएमआईटी भाई
ଭାଇ କାଣ ଖାଦ୍ୟ ଦେଇଥିଲେ ମୁଁ 3 ଦିନ ରହିଛି ନା 3 ଦିନ କହୁଛି 2.5 ଦିନ ରହିଛୁ କାଣ ଖାଦ୍ୟ
पिपीडा आज पण सबुठ बेस्ट
प्रोफेशनल
ତନ୍ମୟ नहीं होला ବିଚାର पाँच मिनट को केते टाइम नहीं गला लंच केतବେଳେ करबे
1:30
एजेंडा कहीं गला
1:30 अबे ग्रुप रे पठाइछि
को
की कंपनी बेटा
CLI
ଫୋନ୍ ଗୋଟେ ଅଛି ଆଉ ଗୋଟେ
CLI
ଏଇଟା ହେବା
257 मुझे आसुनी
ବିପି ଆଗା ମଧ୍ୟ ଥିବ
ପାଖ ହେଇଛି ସେଠି
2V bidirectional amplifier 15-inch mid driver, okay, 12 15-inch.
ଭାଇ ପ୍ଲେସମେଣ୍ଟ ଲାଗିଲାଣି
ମୋର ଡୁଆଲ ଡିଗ୍ରୀ କୋଉ ପ୍ଲେସମେଣ୍ଟ
ଆଉ ଗୋଟେ ବର୍ଷ ଏଠି ଭଲ ଲାଗୁଛି ସବୁ ତାହେଲେ ବିପି ଏଠି ଗେଟ୍ ଫେଟ୍ ଦେଇକି ଅଲଗା କଲେଜ ଗଲନି ଏପଟେ
ଏବେ ଡୁଆଲ ଡିଗ୍ରୀ ତ କରିବି ଏଇଠି ଏକାଥରେ କାମ ସରିବ କାହିଁ କରିବ ଅଲଗା କିଛି କହିଲ କିଏ ପୁଣି ୱେଷ୍ଟ କରିବାର ନାହିଁ ମୋତେ ଟାଇମ୍ ପାଠ ତ ଯୋଉଠୁ କର ଗଭର୍ଣ୍ଣମେଣ୍ଟ ସ୍କୁଲରୁ ପାଠ ପଢ଼ୁ ସେଇ ପାଠ ହିଁ ସେଇ ସାର୍ଟିଫିକେଟ୍ ହିଁ ମିଳିବ ମୋତେ ହଁ ତୁ ଏତେ କ୍ରାକ୍ କରିକି IIT ପଳେଇଲୁ ସେଟା ଗୋଟେ ଅଲଗା ଜିନିଷ ଏବେଟା କେଉଁଠି ଏବେ କିଛି ଗୋଟେ ୱେବସାଇଟ୍ ଖୋଲିଛୁ କିଛି ଗୋଟେ ନାହିଁ ଏମିତିକି ଏଇଟା କେଉଁଠି ଗୋଟେ ଅର୍ଡ଼ର ଦେଇ ବି ପାରିବେନି ପ୍ରାଇସ୍ ବି ଦେଖିପାରିବେନି ଏବେ କୁଏଟ୍ କ'ଣ କରିବେ ଏଠି ଯାଇକି କି କମ୍ପାନୀ କେଜାଣି ପ୍ରଡ଼କ୍ଟର ଆମାଉଣ୍ଟଟା ଦେଇଥିଲେ ଗୋଟେ ଭଲ କହିନଥାନ୍ତା ସେଟା ବି ନାହିଁ ଠିକ ଭାଇ ମନେ ମନେ
ଛୁଆ ଦିଶୁଛି ମାଷ୍ଟର କି ଦିଶ ପାରିବେନି ଗୋଟେ କହୁଛି ପ୍ଲିଜ୍ ଟିକେ ଧୀରେ ପଢ଼
ସେଟା ଯଦି ଫୋନ୍ କରିଦେବି କ'ଣ ଆଚ୍ଛା ଲକ୍ ହେଇଗଲେ ବି ଚାଲୁଛି ଲକ୍ ହେଇଗଲେ ବି ଚାଲୁଛି
କ'ଣ ଓ ଏଇଟା
ଷ୍ଟ୍ରିମିଂଟା ହଁ
ଚାଲିବନି ନା ଆଉ ତୁମେ ଲ୍ୟାପଟପ୍ ଅନ୍ କରି ଷ୍ଟ୍ରିମିଂ ଅନ୍ କରି ପଳେଇଥିବ ସ୍ଲିପ୍ ବି ହେଇଯିବ
ସ୍ଲିପ୍ ହେବନି ସ୍ଲିପ୍ ବନ୍ଦ କରିଦେବା
ସ୍ଲିପ୍ ବନ୍ଦ କଲେ
କ୍ୟାମେରା କାହିଁ ତା ପୋଜିସନ୍ରେ ଅଛି
खोजू भाई
ना এটা তো
तो वेरी स्पेक्टेड था भी देखा
ग्रेट अच्छी
देखा
अब
अपडेट ओ हेटा एंता भी আছে क्या हुआ मैं देखी तो करबो बेटा
खोल लिया
8 बल्ब भी खेलो
हां
8 बल्ब
ଚା ଦଉଛନ୍ତି କି ସେଠି
ନା
ଆଉ
पैसा फेको
ଆଚ୍ଛା ଆଚ୍ଛା ନିଜେ ନିଜେ ପିଅ
ନିଜେ ପିଇବ ଖାଲି ଏକ୍ସପର୍ଟ को ଚାହା ଆଉ ବିସ୍କିଟ୍ ଦିଟା
କୋଉଠି
ଏଟା 5 ଟଙ୍କା
ସେଇଟା କୋଉଠି ଦିଆଯାଉଛି
ଏଟା ତଳୁ ଆଣିକି ତାକୁ ଏଠି ଦିଆଯାଇଛି
ଆଚ୍ଛା ଆଚ୍ଛା
ଆମକୁ କିଛି ମିଳୁନି ଲଞ୍ଚ କରିବ ଯଦି କରିବ ନହେଲେ ପଳେଇବ ଆଜ୍ଞା ସେକେଣ୍ଡ ବି ଚାଲିବ
5:30
କାଲି ଉପରେ ନୂଆ ଏକ୍ସପେକ୍ଟ ଆସିବ କି यही आएगा
କାଲି ପବନ କାଲି ପବନ ସାର୍ ମ୍ୟାଡ଼ାମ
ତୁ ଦେଖିନୁ କି ଏଇଠି ବା ଲେଖା ହେଇଛି
ଗ୍ରୁପରେ ପଠେଇଛନ୍ତି କି
ଏଇଟା ବା ପବନ ସାର୍ ପଠେଇଛି
ମୁଁ ଏଇଟା ମ୍ୟୁଟ୍ କରିଦେଇଛି
କାଲି ଅଛି ମାନସ ସାର୍ ପବନ ଦେନ୍ ପୁଣି କାନୁନ ଗो କି ଗୋଟେ ଅଛି 21 ପୁଣି ମାନସ ଦେନ୍ ପୁଣି 22 ଗो କାନୁନ ଗୋ ଶିବ
ସିଦ୍ଧାର୍ଥ
ସିଦ୍ଧାର୍ଥ 23 ସିଦ୍ଧାର୍ଥ ଅଶ୍ୱିନୀ
ଅଶ୍ୱିନୀ ତମର CS ର ବୋଧେ
କୋଉ ବ୍ରାଞ୍ଚ के ଜାଣି यार ତାହେଲେ ଏତିକି ଜାଣିପାରୁନି
ଅଶ୍ୱିନୀ ବୋଲେ କିଏ ବୁଢ଼ା କି
ଶାଶ୍ୱତ ସାଙ୍ଗ ରୁମ୍ ଯୋଉ ଆସନ୍ତି
ସରି ମୁଁ ଶିବକୁ ଅଶ୍ୱିନୀ ଭାବିଦେଲି ସରି ସରି पवन पढ़ावा मजा लागो देखो तो ब्लेजर पिंधिକି ଆସିତେ କି ନାହିଁ बैक देवे जी
सुपर फीडबैक ଗୋଟେ ସାର୍ଟିଫିକେଟ୍ ଡିଜାଇନ୍ ପାଇଁ କହିଥିଲେ
क्या हुई चाय बिस्किट खाई
खाली एक्सपोर्ट
को बिस्किट 5 टका 10 टका
35 टका गुड डे
200 टका
35
टका
से के कला
और चाह के गोटे ग्लास 2 ग्लास 5 टका पी का खाओ बीड़ी दी देवा ने
सिगारेट
नेगेटिव আসছে
फोटो सेशन तो अभी तो एजेंडा ही नहीं
फोटो सेशन हेलानी ना से फोटो गुड़ा पठाओ परमजीत को डायरेक्ट पठाओ
परमजीत पे किया
परमजीत सर
अच्छी तो से नंबर अच्छी तो पठाओ तो
किया है कि तुम जानने पर नंबर
फोटो नंबर कल्चरल ग्रुप सर अछन
हाँ
कल्चरल ग्रुप
वो छाड़ गोटे काम मत पठी दियो मुझे पठी दूची मतलब तुम थी नंबर नंबर
कल्चरल ग्रुप पड़ेगा फोटो स्वाप फोटो सी फोटो
भाई मत नंबर दिया कॉल करो
परमजीत
हाँ लंबू
तो मत पठी दियो फोन ना ए ना गोटे काम ताकू ही पठास
हाँ
मु नंबर पठी दूस तुम तो मत टे हाई पटेल
भाई 10 टका अब 10 मिनट देवी
मु कोन अंबानी मत तो 10,000 मांगुची
यस और नो भाई अबे नहीं नहीं सकते बे के मते में
जॉब करतले जीजा मागे धाड़ दियो
हमें नहीं मैं करी भी दूज
हां
जॉब नहीं करी भी दूज
तमे भाई
ओ मैकबुक ये दर्जी
भाई से एटा थोड़ी मो कमेर आछी
हां हां
मो कमेर आस्तले M1 नाड नथले M5 आंठल सीधा ये तमे मते हाई पठाओ
नंबर लगा
अरे पता है पड़े
और 943 में पठा 947
अस्मी का
04
943
काना को
04
04
77
तो मु 10 टका देनी के नहीं तो अचंबित कथा कहू मु धीरे रे मना कर चाहिए नहीं नहीं तो का कमी शुभम को मागी 10 मिनट शुभम को मागी दे एबे को नहीं नहीं 2-3 दिन रो पेमेंट हो
फोटो अछि
2-3 दिन रो पेमेंट आसो दे देबी तो देखि गला दुकान जो पचरी देलो छोटी को
8494
हां फिर या इता को मागवा ने हठात कर बोले मैं दे पार फोन किणी जाई छी
अभिषेक हाँ आईफोन लेकिन अब 30
55 टका काको पठाली 55 टका काको पठाई
मत मत
टिपे पे काको पठाली ओ कले आंटी दुकान पेमेंट करते जे एबे नोटिफिकेशन आछी
बोलो
मो डरी मोल गा तो कोडे
बोलो बता
लकी बाप आएगी छो पिला करछो मैं ऑफिशियली पहले किसी प्रॉब्लम नहीं घर को भी किसी नहीं कर पहले मैं आए आई फोन भी पठलो सब मोर फोन सब उठेछो पैसा दे दो स्टोरेज रे
256 जीबी तो
256 46
10 जीबी से दिए ना 10 जीबी दिए ना सी
हां ता गाड़ी भीतर पूरा रही गाड़ी पका भी दे
अरे 10 जीबी के
तो नहीं कर एक्सपर्ट असले डरी जीवा ना पछड़ देगी
10 जीबी के पे दिन फोन तारा सब पे एंड्रॉइड सिस्टम चलेगा 10 जीबी
डाउनलोड ऑल मार दे
की बोल एचडी है ना
वीडियो भी निकल रहा तू ही नंबर बता हाय कॉल ना सेव नहीं कर नंबर में
थैंक यू
पागल कर दो तू ही बोले कॉल कर मुझे
ना वही फोन को खुल दो
जाई छ वीडियो
ना
जाई छ गुटे देखाले +1 वीडियो पर अदे चुतिया चला
Sandeep, send me all the photos and videos.
ए प्रेजेंटेशन लिंक टा ग्रुप पे पठेबा पे कहउछत
प्रेजेंटेशन लिंक प्रेजेंटेशन लिंक कोड आसलानी पे
मु
यूट्यूब रे लिंक कोई पर
हैं प्रेजेंटेशन था ना लिंक न था केमती कुछ
आ पीपीटी रे भाई सेटा तार से लोकटा से लोकटा पचारि दबो ना हम थोड़ी दे देबो का यूट्यूब लिंक पठे छ
यूट्यूब लिंक हम
हां आउथरे पठ दिया
मु सब कॉलेज जति के ऊपर से सब पठे दी क्यों लेफ्ट मार दी
मन तो इच्छा लेने आस गला कोन छ एटी अछि रो
एशियन इंटरनेशनल का अच्छे देखो तो स्कूल लिस्ट दे तो कॉलेज लिस्ट एशियन इंटरनेशनल का अच्छा लीव रहता है पठे दियो कोई पठे दो जोड़ी आउट है भाई मैकबुक से गोटे आईफोन ले धर
धरे धरे आनी डायरेक्ट किछ गोटे प्रो से प्रो आनी देखा जा कोन आनी तो अछि प्रो
18 तो आसपास ना 18
जानी हो तीनटा
कैमरा यूजुअल लोग आना देंगे सब तीन कैमरा कोटी
हां मैंने सही जो नंबर सीरीज को
बस भाई भाई चाह काफी चाहिए इसे क्या हीरो की पीवन तो खबर है बागर पर भी तब मैं पावर पी के मैं इसको
ऑलवेज
ये तो पी टाटा पे ठीक है
कोन आना है
कारण
अभिषेक को आना
दुकान पे ही आसी
कौन भाई
10 टका डाले लिपरा ये कैश और किसी नहीं की जोर कथा कैश इतनी रखो जी सर फसलो
सीधा भरा पड़ेगा सब बड़े उधर भरा पड़े ना ऐसे जाके बैंक रे कैश
कण
भरा पड़े कैश
कैश नहीं ऑनलाइन रखी नहीं पर मुझे रखो के मु 2 मास भीतर 8 लाख ऊपर डिगी देलानी देखने में थी वो 800 थी वो हेलो 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 50 टे दियो जब का रात रे बेगे हिसाब करछो
खर्च नहीं सिस्टम अछि
ये
और सब ठीक है
हाँ
Hello, check, testing, 1, 2, 3.
Oh, hello. नहीं ऑडिटोरियम
अच्छा ठीक
टाइम लगे सब है वहीं पे पोडियम पे
चलता हूँ तभी
फॉर
लेके आ जाए
किसके लिए
पी के आ जाए सब वॉलंटियर्स और स्टाफ
जाओ जाओ पी
स्टार्ट कर दो
तुम हम पी नहीं बेचे
चाय
कॉफी
देते नहीं उसके लिए खत्म कर दे जितना होता है भूलिए पड़े बुझा कोच टिकट वैकेट भी
यूट्यूब रे से ग्रुप रे लिंक टा पठेछि सेटा सेव ही रही छ सब दिन सेटा अपन एक्सेस कर देखिए
कैमरा रोबोट फैमिली एनआईटी ଆମ ସହିତ ଥିଲା ଆମେ ଦିଟା ସାଙ୍ଗ ସହିତ
अच्छा देखिनी माने नहीं ମୁଁ ବି ତ ଏଡୁ ଷ୍ଟୁଡେଣ୍ଟ
ହଁ ବିପିଟି ର ଦି ଜଣ ଯାଇଥିଲେ
should come. Government actually and all those private institutions under this. They are affiliation. They have done this. That is the structure of followed by the principal, faculty, HOD, and faculty. Here, vice chancellor is the head. After that, director, HOD, and regular like that. It's permanent. You can start, sir. They'll come. They'll join.
Okay, let us start.
yes sir
Okay, so next we will derive two factors. One is distribution factor or breadth factor. Another one is speech factor. Distribution factor will come due to the use of this distributed winding. So, induced EMF in full pitch distributed windings, breadth factor, which is also known as distribution factor. So, breadth factor or distribution factor denoted by the symbol KD or KB. Okay. So, here you can see the flux density distribution in a bipolar machine. So, first of all, we have seen that EMF induced in a concentrated full pitch winding is given by this expression. Okay, so that is the induced EMF which is given by any concentrated winding. Now, in place of concentrated winding, if we use distributed winding, what will happen to the magnitude of this EMF? Whether it will remain same or it will be lesser or greater? Okay, it will be lesser due to this use of distributed winding. Okay, so that factor by which it will be lesser, that we are going to derive. So obviously it will be less than 1, so EMF will be less. So here you can see this is the distribution. So in number of slots all the conductors are distributed. So for that, what will happen? We have seen that phase spread. So one EMF, there is a phase shift due to this distribution between two phase EMFs, E1, then E2, E3, like that. So that this phase shift depends on this slot angular pitch, gamma. So it depends on gamma, this value. So it can be 30 degree, 20 degree or something like that. So based on that, the other EMF will be shifted. Okay. So for that, this factor will come. So, and if we take the resultant of all these EMFs, that means let us consider EMF induced by this conductor is E1, then EMF induced by this conductor is E2, and if we add them, then add them means by applying which method, whether it is algebraic sum or Phasor sum, because they are shifted by some angle. So Phasor sum we have to take, algebraically we cannot add them. If we can do that, in that case this magnitude will remain same, but as there is a phase shift, we have to add them using this Phasor addition method, so the magnitude, overall magnitude of the induced EMF will be slightly reduced. So in that case, the factor by which this value will get reduced, that is called the breadth factor, and this EMF has to be multiplied by that factor to get that induced EMF in a distributed winding. So here we have considered this arrangement. So here the slot angular pitch be gamma, and let us consider there are q number of slots per pole. So in each slot there is one winding, one conductor, and each conductor will give its own EMF. So we have seen that when these conductors were in concentrated form, the induced EMF was E. Now we have arranged them in distributed form. So let us assume that in distributed arrangement, the induced EMF by all these conductors be E dashed. So the relation is E dashed equals to E by Q. So each conductor will give you E dashed EMF. Okay. So first one is E dashed. Then what will be the second one? E dashed into that angle. So how we can express that angle? E to the power j gamma. That will give you the phase shift. Okay. So second one is E dashed j omega. In this way, Q number of EMFs will be there, and if we add them in Phasor form, Phasor addition, then we will get this equation. So first one is E dashed 1 into 1, that is E dashed. Second one is J gamma. Second one is, third one is J 2 gamma, because this is the reference. So gamma, 2 gamma, 3 gamma, and so on. In this way, Q number of slots. So finally, final one will give you this induced EMF, E dashed into e to the power J Q minus 1 gamma. And if we add them, we get this expression. This is some geometric progression. So if we add using that formula, we will get this expression. And if we express this exponential form into Cartesian form, we will get cos q gamma plus j sin q gamma, and these two are real part. Same way we can do for this denominator. And if we apply the cosine trigonometric formula, no, before that we can find the real part of that complex expression. We will get this. Now we can apply the cosine formula to simplify this. So finally we will get this expression, E by Q sine Q gamma by 2 divided by sine gamma by 2. And therefore the breadth factor will be this sine Q gamma by 2 divided by Q sine gamma by 2, because E1, that is the Phasor sum of all the EMFs produced by these conductors distributed in Q number of slots. So that induced EMF is reduced from the earlier value when all these conductors were concentrated and giving the induced EMF E. So E will be multiplied by this factor, sine Q gamma by 2 divided by Q sine gamma by 2. So this factor is expressed as KB1. 1 means this is for fundamental frequency only. If we have other frequencies, then we have to write for their expression. I mean, in general, we can write one expression like KBR is equal to sine Q gamma into R by 2 and Q sine gamma R by 2, and so on. So putting the value of R as 1, 3, 5, 7, etc., we can get the corresponding frequency, breadth factor for that particular frequency. So this is the expression for breadth factor for fundamental frequency only. And there are certain advantages of using this distributed winding. So by selecting this gamma and Q, we can eliminate certain harmonics, or at least we can reduce their magnitude. Induced voltage approaches sinusoidal waveform. If the whole waveform is having lesser harmonics, then the waveform will be nearly equal to sinusoid. And armature reaction effect is reduced, so it can reduce the armature effect also. Losses are reduced because if there are harmonics, those harmonics will produce their own losses. So if harmonics are not there, then those losses will not be there, and thereby increasing the efficiency. And also it will provide better cooling, because a concentrated winding, all the turns are accumulated at a single place, so it is very difficult to cool all those conductors. But if they are distributed, naturally they will get cooled.
Sir, what about the amount of copper? Copper saved or
No, copper saving will be done by using short pitched coils only. Distributed winding, it doesn't make any copper saving.
It makes the output waveform equal to the
It reaches nearer to sinusoid, yes, by eliminating certain, or at least by reducing the magnitude of the certain harmonics.
By using this, you are saving the copper, short-pitch winding.
No, by using this short pitch coil, we can reduce the use of copper. Yes,
Because
but
alpha right to the short-pitch factor will be
no. By using distributed winding, we are increasing the amount of copper. Na? If we use concentrated winding.
concentrated winding, the copper is, I think, more.
Oh, obviously. But this distributed winding, in case of you imagine the whole periphery. If we use concentrated winding, most of the peripheral region will remain vacant. So we are not using the whole periphery. But distributed winding, we can place all the conductors all over the periphery. So that is better use of periphery of the armature. That is also one advantage. So now next factor, that is pitch factor. So here you can see so here we can select one pole pitch considering two similar points. So one point is taken here, another point is taken here. So that is one pole pitch distance. At this particular instant of time, the conductors are placed here. So you can see this point is exactly at the central point of this phase belt or band, but it is not like that. It is somewhere before that point. Okay, this is the pole pitch, other point of the pole pitch. So that means we are using short pitched coil. Here we can save copper by using decreasing the length of this overhang or end connection. Okay. So here angle of chord is rho. We can use the other symbol epsilon also. So here this position of this phase band with respect to the initial point is after theta degree. So this center point is after theta degree from this reference point, and from this point to this point it is one pole pitch. From this point to this point it is actually pi minus rho, which is here considered as pi x. Pi minus rho is equal to pi x. That is the arrangement. So angle of chording is rho. So now if we have placed, if we use full pitch coil, then this will be the arrangement. Okay, you can see this is the starting point of calculation of pole pitch, which is exactly at the center of this phase band, and the other point of pole pitch is exactly at the center of this other band. So here, so if we consider one half, this group, one half of the total conductors, then induced EMF in this conductor will be half of E1 obviously, and that can be given by this equation. We have seen this. So E1 equals to this, half of E1 will be half of this, and we have taken this phase spread, which is less than by a pole pitch by a factor x, as we have mentioned here. So this pole pitch is less than by a factor x. So that is why this length is pi x, which is equals to pi minus rho. Okay. So in that case, there will be lesser induced EMF. How much lesser? Let us consider induced EMF in this section. So that is Em by root 2 sin theta. As it is exactly in central position, so it will give you the exactly same amount of induced EMF, which is half of this induced EMF. So that is this part, and the other part, that is the right hand side part, that will be this theta plus pi x. For this section it is only theta, and for this section it is theta plus pi x, and putting the value of pi x as pi minus rho, we can get this. So if these two EMFs are one go, another return, so if we connect these two conductors in series, these two EMFs will get add up, and we will get the sum of these two EMFs across the terminals. So the overall EMF will be given by this expression plus this expression, and that will give you this. And if we apply this sine formula, we get root 2 Em sine theta minus rho by 2 cos rho by 2. So you can see this is the factor by which actually the EMF is getting reduced. So in that case, we can say this pitch factor is cos rho by 2 or cos epsilon by 2, and this is for primary fundamental frequency. If we want to calculate for other frequency, we have to multiply this rho by number of that particular harmonics. So that is R epsilon or R rho for fundamental frequency are equal to 1, for third harmonics are equal to 3, and so on. Now from this formula we can see that we can eliminate certain harmonics by proper designing. Okay, if we want to reduce this third harmonic, then we can place these conductors in such a way that this value of this third harmonics will be equal to 0. That means this 3 rho by 2, that will be equal to 90 degree. Cos 90 is 0. So in that way we can design so that we can eliminate certain harmonics. Normally what we do, we never eliminate any particular harmonics. Because by arranging this way we can eliminate a particular frequency only. So what we do, we select this value of rho in such a way that it will reduce the value of certain harmonic frequencies, more than one. In that way we will select this value of rho. Okay. So that is all about these two factors. So now, after going through those two factors, we can write the modified induced EMF per phase for a distributed short twist winding like EF is equals to 2 pi f n phase kW phi f. So EF, that is the excitation EMF or induced EMF per phase, where n phase is the number of turns per phase, kW is called the winding factor, which is the product of those two factors, that is kd or kb and kp, distribution factor or breadth factor and pitch factor, and phi f is the frequency, flux per pole, and this f is the frequency. So here all the terms are defined. So kW is equals to kd into kp or kb. If we say breadth factor, it is kb. If we say distribution factor, kd. No problem. Okay.
Sir.
Yes.
Some book the derivation for distribution factor and pitch factor are in different way.
Yes.
They are taking the vectors of the induced EMF that are present in a particular slot and they are adding it and find a vectorical sum. Then
given by this three-phase armature winding. So A phase voltage, B phase voltage and C phase voltage, they are 120 degree apart from each other in space as well as in time. Okay, so three-phase balance voltages. So these are the equations by which we can express the three-phase voltages. Yes, these voltages considering ACB phase sequence. If we consider ABC phase sequence, then this angle will be negative, this one will be positive. Waveform, in case of waveform, this VB will come first before VC. Okay, nothing different.
so this is negative sequence. So it is a balanced filtration.
Yes. Yes.
Sir, how can we stop crawling?
Stop?
So it is the phenomenon of induction.
In case of
Crawling induction is the phenomenon of induction product, yes.
Sorry?
how can we stop crawling?
And crawling is not related to signal.
Crawling and crawling, it is related to induction motor.
That will be discussed by some other program of the scaling on from
That is belongs to induction motor.
good task irrelevant.
What problem was that?
Still to this topic.
It is not related to this.
Okay, so now flux and MMF phasor in synchronous alternator, synchronous generator, which is actually armature reaction. Effect of armature MMF on field MMF. That means armature flux on field flux. Whether it will enhance the field flux or whether it will reduce the field flux, that we are going to see. Okay, so at no load, there is no load connected, so there will be no armature current, so no question of armature reaction. As simple as that. So let us draw the phasor diagram. So this is the axis of phase A. So this is one conductor, this is another conductor. So this is the axis of this phase winding A. And A phase axis, okay, and this is the, see, this is the north pole, this is the south pole. So the direction of field MMF or field flux will be in this direction. Flux will come out from this north pole and it will come in this way and enters the south pole, in this way and enters the south pole. That's it. So direction of field MMF will be along this direction. Now FF is field MMF, so that is drawn along this direction, and it will produce flux phi f that will drawn in this direction. Now that is valid if we neglect armature saturation. sorry,
Armature reaction.
no. If we neglect saturation in field poles, okay, that means this field MMF and field flux will remain along the same line if saturation is neglected. Okay, so this flux will induce some voltage in this armature winding and three-phase armature winding. So here whatever we have considered, see, this conductor is facing maximum north pole flux, this conductor is facing maximum south pole flux. So both of them will produce maximum induced EMF based on the position of other conductors or coils B and C. They will induce same induced EMF, corresponding induced EMF, but their values will not be maximum at this position. So if we take the vector addition of all those EMFs, we will find that the resultant will lie along this axis, that means axis of the coil which is having the maximum flux, maximum voltage. So here in this position A is having maximum induced EMF, so resultant will lie along this line. That is one point. Another point is there, that is any induced EMF produced by any flux, that induced EMF will lag that flux by an angle of 90 degrees. That is always true. Mathematically it can be shown. So this EMF EF will lie along this line lagging phi f by an angle of 90 degrees. So we can draw EF along this line.
So field FF is along AA dash and EMF will be
No. Field EMF you don't consider along AA dash. Consider it along SN.
SN.
Pole.
Okay, understood. So EMF here, EMF is a phasor and flux represents current. Flux MMF current is same.
These phasors FF, phi f, they are space phasor. EF is a time phasor. Okay. So here EF is the induced EMF due to main pole flux, that is phi f or FF. Okay, so this is at no load, no armature current, so no question of armature reaction.
So this EF is the AA dash EF, the EMF induced in AA dash.
No. Resultant of all the three EMFs.
Okay.
EA, EB, EC.
Okay.
Since at this instant EA is having maximum magnitude, that is why that resultant will be along the axis of AA dash coil.
Okay.
That is the point. This EF is resultant of all the three induced EMFs. But position will be determined by that condition, that means which coil is having maximum induced EMF at that particular instant. Okay? So next we will discuss armature reaction when the machine will be loaded. So armature current will be there. So this was the earlier situation. Now there will be some armature current. Okay. So we will consider different conditions. Here I have considered only one condition. The other are self-explanatory based on this one. So at unity power factor load. So again, see the situation. EF is here, which is having the maximum induced EMF. So now, since the power factor is unity, resistive load, so the current will also have the maximum value along this A dash conductor. Correspondingly, B dash will have their particular, in that way, the current will be that in those conductors also. So again, the resultant of all those three currents, three phase currents, will lie along this line because it is resistive load, unity power factor. Okay, so we can draw this armature current along EF. Now again, there is one condition. What is that condition? We know that this armature winding must have some impedance, so there will be some voltage drop. So this IA and EF actually in practical situation cannot be along same line. Okay, but IA can be along the same line of VT, terminal voltage. Okay, but here we are assuming that those impedance drops are neglected. That is why we can draw IA and EF along same line. But in practical situation we cannot do this. So now this mark, that is the position when current is maximum, which means for unity power factor load, maximum EMF position and maximum current position both are at the same instant along this same conductor. Accordingly, the other conductors will have their own voltage and current values. Okay. So now, as this is the current, so this current will produce its own MMF, current into number of turns in that particular coil through which this current is flowing, that will give you the MMF. So that MMF will also lie along this line, So that is FA. So let us draw that FA here, and this FA will produce its own flux. So that will be along same line, considering that saturation is neglected. So again, phi A will be along this FA. So now in this air gap, we have two fluxes, phi F and phi A. We have two MMFs, phi F, FF and FA. So what will be the resultant of these two? We can draw the resultant. So this is FR, resultant MMF. Similarly, resultant flux phi R. So now in this air gap, we will have this MMF and this flux. Okay. So here, due to the presence of this armature MMF, the flux has reduced from phi F to phi R. MMF has reduced to phi F to phi R, FR, FF to FR. Okay. So which means the effect of armature reaction at unity power factor is cross magnetizing. Cross means they are in quadrature. Phi F and phi A, they are in quadrature, so the effect is cross magnetizing. Okay. So practically what it will do, it will distort the main field flux or main field MMF, thereby slightly reducing its original value. No as such effect. Simply cross magnetizing, they are in quadrature, so they will distort the orientation, distribution. So next we will consider another condition, considering some lagging power factor load. So let us consider zero power factor lagging load. Lagging means inductive load, zero power factor means exactly purely inductive, 90 degree lagging. Okay, not practical inductance, having some resistive value. So zero power factor lagging load. So initially we will start with this one, which means this this is the FF, that means this N pole and S pole are here. So this A dash will have maximum induced EMF. So that is drawn, lagging that particular flux phi A by an angle of 90 degree. Now since the load is exactly inductive, so lagging by 90 degree, which means this coil A dash will carry maximum current when this rotor will rotate by an angle of 90 degree. That means this north pole will come here. So whatever conductor will be here, in that conductor at that moment there will be maximum induced EMF. At that instant, this conductor A and A dash will carry maximum current. So we can see at this condition maximum induced EMF is at A dash. That is why it is drawn along this line, along the axis of this phase A. And now the rotor has moved by an angle of 90 degree. At this instant, A dash will have maximum current. So this is the maximum current position. That is why it is drawn along this line.
So in this condition, A phase will have minimum EMF.
No, that you cannot say.
Because it is rotated like this, so maximum EMF will be along NS.
Maybe. That is not important here.
Okay. So, but this is zero power factor, you are telling?
Yes. So here, this is current IA, which is opposite to main field flux. So now main field flux is along this direction. So current will be along this direction, and FA will be along this direction. The point is, this FA has to be exactly opposite to that of FF. So that is why it is drawn. Current is drawn in this direction. FA will be along that line, and phi A will also be along that line. So if we subtract this FA from FF, we will get FR. That is the resultant MMF existing in this air gap now. And same way we can draw the flux phi A, and if we subtract that phi A from phi F, we will get the resultant flux phi R. So you can see the reduction, considerable reduction in case of phi F. In this case, phi F will be reduced to phi R. So here the effect of armature reaction is totally demagnetizing. It will reduce the main field flux considerably. Okay. So
can you just once explain why that A dash will have maximum current in this position?
After 90-degree rotation of this, see, induced EMF is having its maximum when this pole was here.
Yeah, yes,
Okay. So as per this condition, exactly lagging load means what?
Oh, this is
current.
lagging. Oh, this is 0 perfect or lagging?
Lagging load. So current will reach its maximum point when? After 90-degree travel of waveform.
Okay.
So when voltage waveform has traveled by 90-degree, then only current will be maximum. So here this pole has reached here. So in this conductor, after traveling 90-degree, whatever conductor is there, that will have this maximum voltage now. But in this conductor, current will be maximum
because
now.
of lagging.
Because of lagging load.
But it is 0 power factor.
Cos 90 is what?
Cos 90 is 0.
0 power factor.
Cos 90 is 0, sir.
Cos 90 is 0, no?
0, yes.
That is why 0 power factor. That is 0 power.
0 power factor. Okay, unity. Okay.
Unity we have discussed. Okay. So here the effect is totally demagnetizing. Now you consider 0 power factor leading. What will be the situation?
In this position?
No, you consider your own position.
Okay.
Next case is 0 power factor leading. What will be the situation?
That improves the magnetic.
Yes, it will enhance the field flux because the direction of IA will be along this line, FA will be along this line. So FA plus FF will give you FR, phi A plus phi F will give you phi R. So effect will be purely magnetizing. Okay. So now the condition point is all these three conditions are ideal condition. Unity power factor load we never have. 0 power factor lagging or leading we never have. What is the practical situation? Somewhat 0.8 power factor lagging. So that we will discuss. Okay. So now we will discuss considering some other power factor. Obviously lagging. So now we will develop the phasor diagram. Phasor diagram means both space phasor as well as time phasor. Okay, and considering this impedance also. So this is the phasor diagram considering lagging load. Okay, so here FF is the field MMF and field flux is phi F. Neglecting saturation, this phi F will induce EF, which will lie along this line, and let us assume some current IA, lagging load. So this IA will lag EF by some angle. So that angle is gamma. We will come later about that angle. Okay. So here we have considered this impedance drop is there. So this IA will lag VT also, the terminal voltage, after subtracting all the voltage drops in this leakage reactance, as well as there will be some other reactance shown here, EA. Okay, so see, FF is field flux that induces this EF. Phi A, that is along IA. See, these two are parallel. FA and IA are in parallel. So this FA is armature reaction MMF that will have its own flux, that is phi A, which is also parallel to FA or IA, and the resultant of this FF and FA will give you phi FR. So due to this FR, this induced EMF is ER. Okay, this ER we will also discuss, and the resultant flux is phi R, that is also in quadrature with this ER. So phi R is producing ER, phi F is producing EF, and this phi A is producing EA. See, this one is in quadrature. is equal to phasor sum of phi f and phi a, sorry, ff and fa, where ff is field mmf, ia is load current which is giving this fa armature reaction mmf, and fr is resultant mmf in the air gap. Now for flux phasor we can have this equation, phi r equals to phi f plus phi a, where phi r is the resultant one, phi f is the main field flux, phi a is armature flux or armature reaction flux, and phi r is resultant flux in the air gap. These three fluxes will produce their induced EMF like EF, ER and EA. So that will have a similar equation. So ER equals to EF plus EA. What is this EF? That is called the stator induced EMF due to the main pole flux, which is known as excitation EMF. Normally we use this term, excitation EMF. Then EA, that is the induced EMF in the armature winding due to armature flux. This will be considered as a reactive voltage drop. Later on we will see this will be considered as a reactive voltage drop. Okay. And ER, that is the air gap voltage drop or voltage behind the leakage impedance. This term I will explain why it is called voltage drop behind the leakage impedance. Okay. So that is the so here you can see EA is considered as a voltage drop. That is why it is negative. From EF we are subtracting this voltage drop to get this ER. Okay, so EA is replaced by this voltage drop, reactive voltage drop. So what is this XA? XA is called armature reaction reactance, not armature reactance, armature reaction reactance. So now ER1, what is this ER1? We can consider this triangle or this whole triangle to write this ER1. So if we subtract this leakage reactance drop from this ER, which was the voltage drop behind the leakage reactance, then we will get one EMF, that is ER1. Okay, so that is called the modified resultant EMF, and XLIA, that is voltage drop in the leakage reactance of the stator winding. So this is physically it is there. IAXA was not physically there. It is considered as a voltage drop. Actually, some voltage will be there, which will reduce this EF to ER. So now putting all these values. So ER was EF minus JIAXA, and this was already here. So if we take common this JIA, we will get XA plus XL. So now both of them are reactants. We can add them to get one single reactance, which is the synchronous reactance. So we can write XS is equals to XA plus XL. That means leakage reactance plus armature reaction reactance will give you the synchronous reactance. And if we now go to this triangle, so VT equals to ER1 minus IAR. Now putting this ER1, expression of ER1, this value, we will get the final expression. So VT is terminal voltage and IAR is voltage drop in the armature resistance only. So this is the final expression, putting expression of ER from this line. So VT equals to EF minus this impedance voltage drop, R plus JXS. XS is synchronous reactance. So this is the impedance drop. So if we subtract this impedance drop from induced EMF, then only we will get this terminal voltage. Okay. So that is EF minus ZS IA. And delta, that is the angle between this VT and EF, that is called the power angle or torque angle. We will derive some expression in relation with this power and torque angle or power angle later. So ZS is synchronous impedance. Okay, so now we will modify this phasor diagram, eliminating this EA and replacing this EA by XA IA and adding this XA and XL to get XS one by one. So see, the whole phasor diagram is rotated by an angle of 90 degree in anti-clockwise direction. So now EF is drawn along y-axis. So this part is the phasor, space phasor, this part is time phasor. So if you are asked to draw the phasor diagram, normally we have to draw this part only, time phasor diagram only. We don't have to draw this part.
So we are taking also the IA as reference.
No.
In some book it is there like this.
No, that I will come. It is required. Somewhere VT is taken reference, somewhere IA is taken as the reference. Where it has to be taken in that way, that I will discuss.
Especially for voltage regulation, we are doing like this.
No. In different method, it is in different way. In EMF method, VT is taken as the reference. In MMF method and ZPF method, IA is taken as the reference. And there is logic behind that. I am coming. So now we can write this ER as VT plus IAR plus JXS. Now see, all the this direction of these phases have changed. Now they are added to VT. So side has changed, therefore their direction has also changed. Earlier this was from this point to this point and it was considered as negative. It means it was subtracted from this EF. Now it is added to VT. These two and these two. I mean this one and this one also. So EF equals to ER plus JIXA, and adding these two we get EF equals to VT plus IAR plus these two reactive drop, and taking common same way we can replace this XA and XL by one reactance, that is XS. So accordingly we can modify, see, only one reactance now. So VT plus IAR plus this reactive drop is equal to EF. Up to this, okay? So this is the phasor diagram, only time phasor diagram for lagging load. This is for unity power factor load, and this is for leading load. Okay. So now here the question is, which one is reference? If we want to draw the phasor diagram for all these three conditions for generator, it is better to take EF as the reference and taking its magnitude fixed for all the three conditions. Okay. So in case of generator, VT will lag the excitation EMF by some angle, that is the load angle. Okay. So that is delta. Okay. Theta will change depending on the load condition, whether it is leading, lagging or unity power factor. So here EF is taken as the reference, and reference can be drawn anywhere, whether it is along positive x-axis, along positive y-axis, doesn't matter. Okay. So to draw this one, I mean these three phasor diagram, EF is taken as the reference and its magnitude is taken fixed. And then we have approached in this way that VT will lag EF. So next step is to draw VT lagging EF by some angle. Then draw IA, whether it is lagging or leading or unity power factor. Based on that, you have to select the position of IA. So consider IA, I mean lagging load. So IA will lag VT. So now next step is to draw IA. So you have drawn IA. IAR, that will be in phase with IA. So draw IAR to VT. So this is one voltage, you can add voltage to voltage only. So VT plus IAR, that will give you this point, and this JIXS, that has to be in quadrature with IA or IAR. So then it is drawn from this point to this point. Okay, so you to get EF. For unity power factor load, again after drawing EF, VT is drawn lagging EF by some angle, that is delta. IA will be in phase with VT, IAR will be in phase with IA, and this JIXS will be in quadrature. Same logic. Here also EF and VT. Now here one thing to note, that here the length or the magnitude of VT is greater than EF. That is in power system, you know the effect, Faraday effect. Okay. So when capacitive load or leading load is used, the terminal voltage will rise than that of no load voltage. Okay. So here you will find negative voltage regulation.
And that is synchronous condenser mode. It will go leading power factor.
But that is again motoring mode. Okay. So here you will find this VT greater than EF. So here from this point you have to draw IAR. So IA is now leading VT by this angle theta. That is the power factor angle. So draw IAR in phase with IA. Then from this draw JIXS in quadrature with IAR or in quadrature with IA line. This angle is also 90 degree. Okay. And if you join this point and this point, you will get EF. So EF equals to Vt plus IAR plus this JIAXS. That is the logic. Now I will show the steps. How to draw. EF is drawn. Draw Vt lagging EF by an angle of delta. Then draw IA lagging Vt by an angle of theta. Then draw IAR in phase with IA. That is IAR. Now from IAR draw JIAXS. Now while you will be drawing in copy, it is little difficult to get exactly this point. Okay, so in those cases, how to draw? In that case, we will take Vt as the reference phasor. So here Vt is drawn. Take IA lagging. Then from here IAR is taken. And from here this JIAXS, and join these 2 points to get EF. But in that case, you cannot get this EF fixed length, which I was trying to say in those 3 figures. In different diagram, you will get different EF length. Okay, so all these approaches are okay. Just you have to remember that in generating mode, Vt will lag EF. In motoring mode, you will find Vt ahead of EF. If you replace in all those 3 diagrams, reverse the situation. If you draw Vt in place of EF and EF in place of Vt, you will get the motoring phasor diagram. Okay, now based on this, we can derive the equivalent circuit. So these are the equations. See, Vt, if we subtract IAR from this Vt, we will get this voltage ER1, which was that modified EMF, and from there, if we subtract JIAXL, leakage voltage drop, we will get ER.
MacBook Flex.
Okay, so here you can see IAR plus JIAXL, that is the leakage impedance drop of the machine. That is why ER is called voltage behind the leakage impedance. One term was there, no? So that is why ER is called voltage behind the leakage impedance, because if we subtract this leakage impedance from this ER, we will get this VT. Okay, and this is the final expression. So if we subtract this armature reaction reactance drop, then we will get EF, and from here we can write EF equals to VT plus all these drops.
So the armature reaction XA, physically how it is created, means because of the flux supposing.
See, this is actually a kind of loss. Whatever we are generating, see, we are providing field current to the field winding to produce flux. That flux, what do we expect? We expect whatever flux we are producing by providing field current, the whole flux will give us the EMF. Okay, now we are not getting that. That means what? We are providing current. For that we have to pay, na? But we are not getting the whole EMF. Some of the EMF is actually some of the flux is reduced by this armature reaction, so we are not getting that much of EMF. So we are losing. So that is a kind of loss. In that perspective, you can say in that way. To supply current, we have to pay. There is no other option. But whatever we are paying, we are not getting it back. Okay, so now this open circuit test, short circuit test, and short circuit ratio. So open circuit test is to determine the OCC curve. Short circuit test is to determine short circuit characteristic, and short circuit ratio, one concept that we will discuss. And these two tests are performed to determine the impedance or reactance of the cylindrical rotor machine, ZS as well as XS. Okay. One more test is required to determine the XS. Actually, by this test, we can get ZS only. To separately get this XS, we need to perform this DC resistance test also. Okay. So this is the open circuit condition, you can see. So that equivalent circuit, whatever I have shown you, that is this one is a simplified one. Only one reactance in place of XA and XL. XS is here, resistance, armature resistance R. This is the induced EMF, and open circuit condition, no armature current. So armature current is 0. So that is the open circuit test. So EF equals to Vt plus IF into Ra plus JXS. So this part will be 0, which means if we connect some voltmeter across here, we will get EF actually. So that is Vt 0, no load voltage at open circuit condition. And if we neglect R, EF equals to this R will not be here. And under open circuit condition, IA is 0, so EF equals to Vt 0, no load voltage, which is excitation EMF. And under short circuit condition, there is a dead short circuit, so this Vt is 0. In that case, EF equals to Vt plus IA into JXS, so this Vt is equals to 0. So EF by IA will give you JXS. If you do not neglect R, you will get ZS here. Okay, so this condition will give you approximate value of XS. Normally the value of RA is very small, so this is practically we can a considerable approximation. We can consider like this. Okay, so that will give you XS. If we do not neglect RA, you will get ZS by this equation. Okay. Now how to perform this test? So open circuit test, to get open circuit characteristics, that is OCC. So this is the circuit arrangement, you can see. This is 3-phase winding, some voltmeter is connected, which is equivalent to keeping these terminals open. And this is the field circuit where some rheostat is connected to vary the field current. We need to vary the field current to get this OCC at different points. So here IF is the armature field current. So this ammeter will record IF, and this voltmeter will record the induced EMF, that is Vt0 or EF. Okay. So first of all, how to run this machine? Keep the output terminals open. So it is open circuited, and the machine is run at constant rated speed. This is important. So if you want to get the OCC at rated speed, then you have to run the machine by at rated speed by some prime mover, maybe some DC machine or DC motor or induction motor, whatever. And the field current IF is increased in steps. So by this rheostat, you can vary the field current. Okay. And you have to take this voltage reading from this voltmeter, that is Vt0, which is EF, and this field current you have to record. And every step, if you have to check whether the speed has changed or not. If the speed has changed, then you have to, by changing, controlling the prime mover speed, you have to again get back to this earlier speed, that is rated speed, and at that condition only you have to take reading. You have to keep this speed fixed. Maybe it is at some other speed, that is also okay, but that will not be the rated OCC. If you want rated OCC, then you have to run the machine at rated speed only.
Do you use the flux control method to control keep the speed at a particular value of the prime mover?
How?
If the prime mover is a DC motor, then you have to arrange a flux control method.
Yes. By controlling the speed, I have mentioned, by controlling the speed of the prime mover.
Flux control. So the rated speed of the alternator is mentioned in the nameplate.
Yes.
So this is treated as the rated.
Yes.
So it was a mistake. So
sorry?
No. So while we are performing an experiment, so the old machines are there set. So
no, you can perform this experiment at some other speed also, but that will not be the rated OCC.
Okay.
You will find the OCC.
You will have a OCC, but it will not.
At rated condition is you have to maintain that speed.
Maintain that speed.
That is the condition. At different speed you will get different OCC. That is okay. So now plot IF versus EF to get the OCC, and the OCC will look like this. So it has some linear portion when there is no saturation. Then after a certain value of field current, saturation sets in, and the OCC will take the shape like this. This non-linear part will come. Okay. Now the SCC, almost similar arrangement. Only in place of voltmeter, you have to connect one ammeter, and the other terminal also has to be shorted with that. So this is dead short circuit. Okay, and this field circuit arrangement remains same. Now here you don't have to maintain this speed. There is no requirement. You can do that, but there is no need. You can start the experiment at rated speed. Then you have to vary this field current, and you have to take this ammeter reading and this ammeter reading without bothering the speed of the machine.
But
Okay.
here we have to keep the record of the emitter that is connected to the stator side, because the stator has a specific current limit.
No, that I'm coming.
Otherwise, the stator will burn.
So here keep the terminals shorted using this ammeter, and the other terminal has to be connected to those two. Though not mandatory, but still you can run the machine near its rated speed. The field current IF is increased in steps like the previous case, and we can go up to 120% of the rated value of field current. Beyond that we cannot go, otherwise the machine will burn. Okay. And one more thing, you have to take all these readings very quickly. Otherwise there will be so much heating that machine will burn. Okay. So one thing you have to note, that you cannot go beyond this 120% of rated current value. Suppose the rated current field current is 10 ampere, so you can go up to 12 ampere. Beyond that you cannot go, and mostly the last of the few readings you have to take very quickly. Okay. So now you have to plot this IF versus ISC to get the short circuit characteristics. That is a straight line. There is no question of saturation. Okay. If we draw these two together, how these two curves will give us ZS or XS, that now we have to discuss. Okay. So we will draw these two curves on the same plot, same graph paper, using same axis. Only difference is, along this line we have already selected this one as for induced EMF, that is in volt. So we cannot plot ISC taking this one as the other ISC axis. So we have to draw one more axis, whether it is here or somewhere here, no problem. So this is ISC axis in ampere. This one is common. Okay, and we have to select the scale in such a way this OCC must remain above SCC. Due to the selection of a scale, this SCC can go exactly coinciding this OCC part, linear part above OCC. Okay, that will create some misconception. You must suggest your student to select the SCC in such a way, select the scale in such a way that SCC comes below this OCC. Okay, so after drawing this plot, how to calculate ZS? First, select one field current value. This part is tricky. One can select field current here, that will be in linear zone of OCC. One can select field current here, that will be in saturation zone. Okay, then what to select? Try to select this field current in this zone, that is the knee zone, not in linear zone, not in saturated zone. It is in non-linear, where the non-linearity starts. That will give you a moderate value, not unsaturated value, not saturated value of excess. Okay, so here you have selected one field current value. From there, draw a vertical line that will intersect SCC at some point and OCC at some other point. From this point, draw a horizontal line that will intersect this y-axis or EF axis at some point, and from this point you have to draw another horizontal line that will intersect this ISC line at some point. So what is this voltage? This voltage is induced EMF at this field current. What is this current? This current is short circuit current at this field current. Take the ratio of these two, you will get ZS. Okay? So ZS is this open circuit terminal voltage for a certain field current value. See, certain field current value. This selection is on you. You can select the field current. And short circuit current for the same field current value. Whatever field current you have selected, you have to take the voltage as well as current at that same field current value. Okay. Now, short circuit ratio. This is actually a ratio of two field currents. Earlier, that ZS was a ratio of one voltage and one current. Voltage induced EMF and current, that is armature current. This short circuit ratio is ratio of two field currents, not induced EMF or armature current. It is the ratio of two field currents. Which two field currents? One field current which will give you rated open circuit voltage. Another field current which will give you rated short circuit current. Take the ratio of these two currents, you will get the short circuit ratio. Okay, so SCR, that is OP by OQ. What is the importance of this short circuit ratio? It is an indicator of the performance of this synchronous machine. It is actually reciprocal of saturated synchronous reactance. Okay. So if SCR value is high, which means the synchronous reactance is less. Lesser synchronous reactance, what will give you? Lesser synchronous reactance will give you lesser voltage regulation. Lesser voltage regulation means much more stability. It will give you stable voltage. Voltage will not fluctuate too much. And higher SCR means, lower SCR means higher synchronous reactance. Higher synchronous reactance means higher value of voltage regulation means higher fluctuation. Okay. So from SCR, short circuit ratio, we can guess the performance of the synchronous machine. So if there were no saturation, ZS would be constant, but there is saturation. So this is the variation of ZS based on this saturation. That means if we select some field current here, it will give you some ZS value here, which is very high, unsaturated value. If we select some field current here, that will give you ZS value which is much less, so which is saturated synchronous impedance. So we have to select this field current which will give you the ZS value somewhere here. Okay, so since this, if we normally we apply this method to calculate voltage regulation using EMF method. So as this selection of field current is very critical, and based on that we may get different values of ZS. So the whatever voltage regulation we will get from EMF value, that is not exact value and that is not very accurate, but we can guess, we can get an idea what will be the range of this voltage regulation. That is why this method, this EMF method, is called optimistic method. Sorry, pessimistic method. Okay. So now ZS equals to this R plus JXA. So we have determined ZS. If we can determine R somehow, but maybe by using some multimeter, we can measure the resistance of the armature winding. Then we can calculate XS using the formula ZS square minus R square root under, or we can perform some DC resistance test. And based on that, I mean, there are two possibilities of connection, whether it is this armature winding, it can be star connected or delta connected. Based on that, RDC value will be this for star connection, and for delta connection, this will be this. I think you have the idea why these are like this. That can be shown by drawing the connection diagram only. Okay. So this DC resistance is actually, synchronous machine is an AC machine, but we are getting some DC resistance, and DC resistance is less than that of AC resistance due to this skin effect. You know this. So we need some multiplying factor. So to get the AC value, that is R, we have to multiply this RDC, whatever we have got from this DC resistance test, by this factor 1.2 to 1.3. Any value, multiplying this, I mean selecting any value in between these two values, we can get this armature resistance per phase, and then we can calculate XS using that formula. So XS equals to root under this square minus this square. Okay. Now the zero power factor characteristics from which we will get the Portier triangle. So this is the general, this Portier, sorry, any doubt, any question? this voltage regulation calculation, here I will discuss three methods. One is EMF method, another is MMF method, and third one is Portier reactance or Portier triangle method, that is also known as zero power factor method. So out of those three, this one is the most generalized one, and it will give you more or less correct voltage regulation value. Okay, so that is why it is important to know how to get this Portier triangle, how to draw this Portier triangle. So here XS equals to XA plus XL, we know this, armature reaction reactance plus leakage reactance. Okay, so what is this zero power factor characteristic? Zero power factor characteristic is a plot between terminal voltage Vt and field current under full load and zero power factor condition. Okay. So here we will take the terminal voltage under full load condition. So how we can do that? So zero power factor can be used to determine the armature reaction and FA and leakage reactance XL. Actually, to calculate the voltage regulation, we need this leakage reactance drop. We don't require this XL separately. For voltage regulation calculation, we need IAXL only. That is sufficient. But from there, if armature current is known, we can calculate XL also. So this is the arrangement. So here you can see one voltmeter is connected, and this is three-phase inductive load, zero power factor. So we have considered lagging zero power factor. So purely inductive load, we can say. And this arrangement is similar to that of OC test or SC test. So first, run synchronous machine at rated speed by prime mover. Connect the purely inductive load across the armature terminals and increase the field current till rated armature current flows. So first of all, we have to drive the rotor by some prime mover at rated speed. Then we will connect this inductive load. Then we will put on the DC supply to the field winding and vary this rheostat to supply that much of current which will circulate rated current in the armature. Okay. Now we will vary this load. As soon as we vary this load, this current through this armature will no longer remain its rated value, at its rated value. So again we have to adjust this rheostat to bring it back, that means that armature current, to bring it back its rated value. So we will change this inductive load in step. There will be a change in armature current. We have to bring it back to its rated value by adjusting this rheostat. Then we will take the reading of this Vt and this IF. In this way, we will take several readings and then we will plot this IF and Vt. So we have to, here we have to fix the armature current at rated value. Though we are changing load, as soon as we change the load, armature current will change. That is obvious. But by adjusting the field rheostat, we will bring it back to its original rated value. Then we will take the reading of Vt and IF, and that will be plotted to get the zero power factor characteristic. So this is the zero power factor characteristic, which is similar. I mean, its shape is similar to that of OCC, but it will not pass through the origin. Okay, and this is the phasor diagram at zero power factor lagging condition. You can see FA is opposite to FF. We have seen this. It is demagnetizing, so that is why FR is less. So it is almost in phase opposition to FF. So FR, and this is VT. This is IAR, which is in phase with IA, and this is only leakage reactance drop. XA is not included here. And from there we will draw the Portier triangle. So this VT, from VT we have to draw one horizontal line. Horizontal line, and that will intersect ZPFC at some point. and from there we will drop on vertical line to get some field current value here. From here we will draw another horizontal line that will intersect OCC at some point. So this we will connect this point and this point, and some vertical line from this point to this point. Okay. So this ABC is Portier triangle. So this BC length, that is IAXL. How we can say this is IAXL? Because this drop, IAXL drop, is almost perpendicular to IA. That is why we can say this length is IAXL. And this point to this point, this AB, that is actually FA, field current to produce this, armature reaction field current. Armature reaction MMF. So that is Portier triangle. Using this Portier triangle, we will determine the voltage regulation. And while we will be calculating voltage regulation, how this Portier triangle will be drawn, that will be discussed in more details. Okay. Here, just you have to identify what is this Portier triangle. Okay. So next is voltage regulation. So first of all, what is voltage regulation? Voltage regulation can be defined as the change in terminal voltage expressed as a percentage or per unit of the rated voltage when the load at a given power factor is removed with speed and field current remaining unchanged. So when probably you have also experienced the same, that whenever we ask this question to a student, he simply replies that it is defined as the change in terminal voltage as a percentage or per unit of the rated voltage, nothing else. But without this condition, that definition is invalid. He or she must have to mention this condition. That means when the load at a given power factor is removed with speed and field current remaining unchanged. That means some generator, synchronous generator is running at some loaded condition. If we, at that condition, we will get some terminal voltage. If we remove that load, its terminal voltage either rise or it will fall based on what type of load was there, connected there. If it was capacitive load, terminal voltage will fall. If inductive load was connected, terminal voltage will rise. Okay. So without this condition, that voltage regulation definition is invalid. Okay. So we can mathematically calculate using this formula EF minus VT by VT. So voltage regulation calculation using this formula is very easy. We will have EF, VT, then we will apply this formula to get here. Then why we are using all those methods? Those are graphical methods and very difficult to find voltage regulation using those methods. Why we are using those methods? That is the question. Actually, VT, that is nameplate data. It is okay, easily available. How you will get this EF? Normally, these synchronous machines are very big in size. Lots of loads are connected to those machines. Okay. Now, if this load is suddenly removed, there will be a sudden rise. Normally, loads are lagging, so voltage will rise. Now, if the voltage rises to that level, there will be many detrimental effect on that machine. Insulation may get damaged, the whole machine may get damaged. Okay. So normally we cannot allow to remove that whole load. Okay. So in that case, how to get this EF? There is no way to get that EF. For that we need some indirect method to calculate this EF. After we get EF, then we will be able to apply this formula. Okay. So that is why we need this indirect method. There are many methods. And next question is, why do we need to know voltage regulation? The reason is obvious. If suddenly, accidentally, all the loads get disconnected, then how much this voltage will rise? That we must know beforehand. Otherwise, we cannot design the insulation for the windings. Okay. And some other reasons are also there, like if we know the range of voltages, full load rated voltage to no load voltage, if we know this range between which two voltages this voltage may fluctuate, we can design the automatic voltage regulator also. If the voltage slightly rises, the automatic voltage regulator will down the voltage automatically. Okay. So to design this automatic voltage regulator, we must know these two ranges. And steady state short circuit conditions and stability are also affected by this voltage regulation. As you have seen, this short circuit ratio, that value determines the type of voltage regulation, whether it is high or low. Parallel operation of alternator, that is also affected. If you have two synchronous generators connected in parallel having two different, their voltage regulations differs too much, then you cannot connect them in parallel. Okay, their voltage regulation has to be nearer to each other. So how to calculate this voltage regulation? There are different methods. 3 methods are included here. So EMF method or synchronous impedance method, MMF method, zero power factor or Portier reactance, or triangle method. Bhavan, it is time to take a break. Okay, so after lunch we will discuss these things.
सर डिस्कनेक्ट करके दे देना, रिजेक्ट करके दे देना। सर गोटे रिजेक्ट करके दे दीजिए। सर कमेंट कर दिया अपन ना छोड़ दो, मैडम दे दीजिए।
Lunch is provided.
Lunch is provided in the canteen.
Where? Let the session finish. End of this program.
ସାର୍ ଖାଇବାକୁ ଗଲେଣି?
Sir, have you taken lunch?